For decades, scientists have accepted the Big Bang theory as the main explanation for how the universe began, placing the start of space and time nearly 14 billion years ago. The James Webb Space Telescope has extended our observations further than any previous instrument. It has detected galaxies that appear older than expected, forming when the universe was still very young, and structures that do not fit the timeline predicted by the Big Bang. Could our most accepted explanation for the universe's beginning be incorrect? Could the James Webb Space Telescope be changing our understanding of the earliest moments of cosmic history? Before we continue this journey, comment below where in the world you're watching from and what the time is there now. We're always excited about hearing where in the world our viewers are tuning in from. The James Webb Space Telescope, often called Webb or JWST, is one of the most advanced astronomical observatories ever built. It was designed and constructed over more than 2 decades by an international collaboration led by NASA, in partnership with the European Space Agency and the Canadian Space Agency. Its creation involved thousands of scientists, engineers and technicians working across the globe, combining expertise in optics, electronics, materials science and space engineering. The goal was to build a telescope that could see deeper into the universe than any previous telescope, including the Hubble Space Telescope, which had already transformed human understanding of galaxies, stars and planetary systems. Unlike Hubble, which observes mostly invisible and ultraviolet light, the James Webb Space Telescope is primarily designed to observe the universe in the infrared spectrum, which allows it to detect heat emitted by very distant and faint objects. This makes it possible for Webb to look further back in time, essentially observing the first galaxies and stars that formed after the Big Bang, and to study planetary systems around other stars, including their atmospheres and potential habitability. The design of the James Webb Space Telescope is both ambitious and intricate. It is centered around a large primary mirror that spans 21 feet and 4 inches in diameter, composed of 18 hexagonal segments made of ultra-lightweight beryllium metal coated with a thin layer of gold. This mirror is significantly larger than Hubble's primary mirror, which is only 7 feet and 9 inches across. The size and shape of Webb's mirror allow it to capture much more light from distant objects, increasing its sensitivity and resolution. The mirror's segments are adjustable using tiny actuators, which enable scientists to fine-tune their alignment with incredible precision after launch. This is crucial because Webb cannot be serviced in space like Hubble was, so everything must work perfectly after it reaches its final orbit. To protect the telescope's sensitive instruments from heat and light from the Sun, Earth and Moon, Webb has a sunshield the size of a tennis court. This sunshield is composed of 5 layers of a special material called Kapton, which is coated with aluminum and doped silicon to reflect sunlight and maintain extremely cold temperatures on the side of the telescope where the instruments are located. The layers are carefully separated to allow heat to radiate away, keeping the telescope cold enough for its infrared detectors to function optimally, because even a small increase in temperature could interfere with the detection of faint cosmic signals. The instruments on board the James Webb Space Telescope are designed to cover a wide range of astronomical observations. The Near-Infrared Camera, or NIRCam, is Webb's primary imaging instrument, capable of detecting light from the earliest galaxies and star-forming regions. It can also observe the atmospheres of exoplanets, allowing scientists to study the composition, temperature and potential chemical signatures that could indicate habitability. The Near-Infrared Spectrograph, or NIRSpec, complements NIRCam by dispersing light into its component wavelengths, allowing precise measurement of chemical compositions, redshifts, and other key properties of distant objects. The Mid-Infrared Instrument, or MIRI, extends Webb's observations into longer wavelengths, enabling the study of cooler objects such as forming planets, distant comets, and the dust and gas in galaxies that are hidden from optical telescopes. Webb also includes a fine guidance sensor, a near-infrared imager and slitless spectrograph, which are crucial for maintaining the telescope's pointing accuracy and for specialized observations of stars and exoplanets. The mission objectives of the James Webb Space Telescope are broad and revolutionary. One of its primary goals is to investigate the first light and earliest galaxies in the universe. By observing light that has travelled for more than 13 billion years, Webb can reveal how the very first stars ignited and how the earliest galaxies formed, evolved, and merged to create the large-scale structures seen today. These observations help answer fundamental questions about the origins of cosmic structure and the processes that led to the universe as we know it. Another major objective is the study of star and planet formation. Webb can peer into dense clouds of gas and dust where stars are being born, revealing the initial stages of stellar evolution and the formation of planetary systems. By studying the physical and chemical conditions in these regions, scientists gain insights into how common planets like Earth may be throughout the galaxy. Webb is also designed to explore exoplanets, planets orbiting stars beyond our solar system. By observing the light that passes through an exoplanet's atmosphere, or the light reflected from its surface, the telescope can identify molecules such as water, carbon dioxide, methane, and oxygen. This provides crucial information about the planet's composition and potential for supporting life. Unlike previous telescopes, Webb's infrared capabilities allow it to penetrate thick clouds of gas and dust, revealing planets and planetary systems that were previously hidden. It can also study the interactions between stars and their surrounding disks of material, providing clues about how planets acquire their atmospheres and evolve over time. To achieve these objectives, the James Webb Space Telescope operates from a special orbit around the Sun known as the Second Lagrange Point, or L2, located approximately 1 million miles from Earth. This location provides a stable environment with minimal interference from Earth's heat and light, allowing the telescope to maintain the low temperatures necessary for infrared observations. Unlike telescopes in low Earth orbit, Webb's position at L2 offers a clear and continuous view of the universe without frequent interruptions from Earth's shadow. However, this orbit also means that the telescope cannot be serviced or repaired by astronauts, so every component must function reliably for the expected mission lifetime, which is at least 10 years. The engineering challenges involved in building and launching the James Webb Space Telescope were immense. Every part of the telescope had to be tested rigorously to ensure it could survive the harsh conditions of space, including the extreme cold, vacuum, and radiation. The telescope's components were folded and compacted for launch aboard an Ariane 5 rocket, which required precise engineering to ensure that the sun shield and mirror segments could deploy perfectly once in space. The deployment sequence involved hundreds of separate mechanisms operating in exact order, including the unfolding of the sun shield, the extension of the primary mirror, and the alignment of the mirror segments. Even a minor error could have jeopardized the mission, so engineers developed elaborate simulations and testing procedures on Earth to verify every step. The data collected by the James Webb Space Telescope are transmitted back to Earth using high-frequency radio signals. These signals are received by NASA's Deep Space Network, a collection of large radio antennas located in California, Spain, and Australia. The data are then processed, calibrated, and made available to scientists worldwide, enabling a global effort to analyze the findings. Webb's observations are expected to generate a massive volume of information, including detailed images, spectra, and time series data that allow researchers to study dynamic processes such as supernova, variable stars, and the growth of galaxies over cosmic time. The telescope's open data policy ensures that astronomers from many countries can collaborate, compare results, and expand humanity's understanding of the universe. The James Webb Space Telescope is not only a tool for studying distant galaxies and exoplanets, but also a key instrument for understanding the evolution of our own Milky Way galaxy. By observing star clusters, interstellar gas clouds, and regions of active star formation, Webb provides a detailed view of the processes that shape galaxies over billions of years. It can measure the distribution of chemical elements in stars and gas, offering clues about how successive generations of stars enrich the cosmos with heavier elements necessary for planets and life. In addition, Webb can investigate the behavior of black holes and other complex objects at the centers of galaxies, helping scientists understand their role in galactic evolution and structure. One of the revolutionary aspects of the James Webb Space Telescope is its ability to conduct time-domain astronomy, which involves repeated observations of the same objects over time. This allows researchers to study transient events such as exploding stars, stellar flares, and the variable brightness of distant galaxies. Observing these phenomena in infrared light provides new insights into the physical processes driving them and how they change over periods ranging from minutes to years. The telescope's sensitivity also enables the detection of extremely faint objects that were previously invisible, revealing new populations of stars, galaxies, and planetary systems that challenge existing theories of cosmic evolution. The James Webb Space Telescope represents a remarkable achievement in international cooperation, combining advanced technology, scientific ambition, and human ingenuity. Its discoveries are already reshaping our understanding of the universe, revealing galaxies that formed surprisingly early, stars with unexpected properties, and planetary systems that are more diverse than previously imagined. By studying the universe in unprecedented detail, Webb is answering long-standing questions about the origins of galaxies, stars, and planets, while also raising new questions that will drive scientific research for decades. Its observations are expected to have far-reaching implications not only for astronomy, but also for fields such as planetary science, astrophysics, and cosmology. Every aspect of the James Webb Space Telescope, from its gold-coated mirror segments to its multi-layered sun shield and sophisticated instruments, was designed to maximize the telescope's ability to capture faint infrared signals from across the universe. Its ability to observe in infrared allows it to look through cosmic dust clouds, see cooler objects, and detect light that has been stretched to longer wavelengths by the expansion of the universe. This enables Webb to study the first stars, the formation of galaxies, the structure of planetary systems, and the chemical composition of exoplanets. Each of these observations contributes to a larger picture of the universe's history, the life cycle of stars, and the processes that create planets capable of supporting life. The telescope's mission has already led to remarkable discoveries, including the detection of some of the most distant galaxies ever observed. These galaxies appear as they were only a few 100 million years after the universe began, providing direct evidence of the early stages of cosmic evolution. Webb has also observed intricate structures within nearby galaxies, such as spiral arms, star clusters, and regions of intense star formation, giving astronomers a more complete understanding of the physical processes shaping galactic environments. In addition, its observations of exoplanets have revealed complex atmospheres, unusual chemical compositions, and potential signatures of water and other molecules essential for life, expanding the search for habitable worlds beyond our solar system. The James Webb Space Telescope is expected to operate for at least 10 years, during which it will continue to push the boundaries of human knowledge. Its data will help scientists refine models of cosmic evolution, understand the formation of galaxies and stars, and explore the diversity of planetary systems. By observing the universe in infrared light, Webb provides a unique perspective that complements other space observatories and ground-based telescopes, creating a more complete picture of the cosmos. Its discoveries are already influencing how scientists think about the origins of the universe, the development of galaxies, and the potential for life on other planets, and they will continue to do so for decades to come. The development of the James Webb Space Telescope was not without challenges and delays. Originally conceived in the early 1990s, the project faced numerous technical, budgetary, and logistical obstacles over its 30-year journey to launch. Complexities in designing the deployable mirror and sunshield, coupled with the need for unprecedented thermal and optical precision, led to multiple redesigns and rigorous testing cycles. The launch itself, conducted aboard an Ariane 5 rocket from French Guiana, required careful coordination between international partners, as the folded telescope had to survive the forces of liftoff, the vacuum of space, and the precise unfolding sequence once it reached its orbit at L2. Despite these hurdles, the successful deployment of Webb marked a historic achievement in space exploration and engineering, demonstrating the capabilities of modern technology and international collaboration. Webb's observations are expected to transform many areas of astronomy. In the study of distant galaxies, it will reveal the formation and growth of structures in the universe, the role of dark matter and dark energy in shaping cosmic evolution, and the distribution of elements produced by successive generations of stars. In the study of stars and planetary systems, Webb will provide unprecedented detail about the birth, life, and death of stars, the processes that form planets, and the chemical environments that may support life. Its study of exoplanets will help answer one of humanity's most profound questions: whether life exists elsewhere in the universe. By analysing the atmospheres of distant worlds and detecting chemical markers associated with life, Webb contributes to the ongoing search for habitable planets and the understanding of planetary habitability in diverse stellar environments. The James Webb Space Telescope also plays a key role in complementing and extending the discoveries made by other telescopes, including Hubble, Chandra, and future missions such as the Nancy Grace Roman Space Telescope. Its infrared observations provide a different perspective, allowing astronomers to see objects and processes that are invisible in visible light. This synergy between telescopes operating in different wavelengths enhances the overall understanding of the universe, providing a multi-dimensional view of cosmic phenomena and the processes that govern their behavior. Webb's ability to peer into regions previously hidden by dust, detect faint and distant objects, and measure precise chemical compositions establishes it as a cornerstone of modern astronomy. In terms of outreach and education, the James Webb Space Telescope has already captured the public imagination, inspiring curiosity and wonder about the universe. Its breathtaking images of distant galaxies, nebulae, and planetary systems are not only scientifically valuable, but also visually stunning, bringing the beauty and complexity of the cosmos to people around the world. The telescope's mission demonstrates the power of human ingenuity, international cooperation, and the pursuit of knowledge, serving as a symbol of what can be achieved when nations and scientists work together toward a common goal. These images, data, and discoveries provide educational resources for students, educators, and the general public, fostering interest in science, technology, engineering, and mathematics, and encouraging future generations to explore the universe. The James Webb Space Telescope is equipped to continue making discoveries far beyond what was originally envisioned. Its instruments are capable of adapting to new scientific questions, whether that involves the detection of faint galaxies at the edge of the observable universe, the monitoring of dynamic processes in stellar nurseries, or the characterization of newly discovered exoplanets. The telescope's versatility ensures that it will remain at the forefront of astronomical research, producing data that challenge existing theories, reveal new phenomena, and provide a deeper understanding of the universe. Each observation adds to a growing body of knowledge, helping scientists refine models of cosmic evolution, improve predictions about the behavior of stars and planets, and understand the mechanisms that drive galaxy formation and growth. In addition to its technical achievements, the James Webb Space Telescope represents a triumph of careful planning, innovation, and perseverance. Its long journey from concept to launch involved overcoming seemingly insurmountable obstacles, from the engineering of deployable mirrors and sunshields to the coordination of international partners and the rigorous testing required to ensure its success. Every detail of the telescope, from the alignment of mirror segments to the cooling of its instruments, reflects a careful balance between scientific ambition and practical engineering. The mission embodies the idea that exploration requires patience, meticulous preparation, and a willingness to push the limits of what is possible. By successfully deploying and operating in space, Webb has set a new standard for astronomical observation and opened the door to discoveries that will shape our understanding of the universe for generations. Webb's observations are already challenging preconceived ideas about the universe. Some of the galaxies observed appear to have formed much earlier than models predicted, suggesting that the processes of galaxy formation and growth may be more complex and rapid than previously thought. Observations of exoplanet atmospheres are revealing chemical compositions and physical conditions that were unexpected, providing new insights into the diversity of planetary systems. By detecting faint objects and phenomena previously hidden from view, Webb continues to expand the known boundaries of the observable universe, showing that there is still much to learn and discover. Its data also provide critical input for theoretical models, helping scientists refine their understanding of cosmic evolution, the life cycle of stars, and the potential for habitable environments beyond our solar system. The James Webb Space Telescope's capabilities are unprecedented, from its large, gold-coated mirror to its multi-layered sunshield and sensitive infrared instruments. Its ability to observe distant galaxies, star-forming regions, and exoplanet atmospheres in remarkable detail represents a quantum leap in observational astronomy. By observing the universe in infrared light, it can detect objects too faint, distant, or obscured for previous telescopes. This allows scientists to answer fundamental questions about the universe's origins, the formation of stars and planets, and the potential for life elsewhere. Webb's mission is not limited to one area of research. It spans cosmology, galactic evolution, stellar physics, planetary science, and astrobiology, providing a comprehensive platform for exploring the universe in ways that were previously impossible. Webb's success is the result of careful collaboration, engineering precision, and scientific vision. Every aspect of the telescope, from its deployment mechanisms to its instruments and orbital configuration, was meticulously planned and tested to ensure it could meet its ambitious objectives. Its launch, deployment, and early observations demonstrated that decades of planning, innovation, and international cooperation had paid off, enabling a telescope capable of observing the universe with unparalleled clarity. As Webb continues its mission, it will provide an ever-growing data set, helping scientists make sense of the universe's earliest moments, the formation of galaxies and stars, the behavior of exoplanets, and the physical processes that govern cosmic structures. Each new observation adds to a richer, more detailed understanding of the cosmos and our place within it. The James Webb Space Telescope is poised to remain a cornerstone of astronomical research for many years. Its ability to see the universe in unprecedented detail, observe phenomena that were previously invisible, and study the earlier stages of cosmic history ensures that it will continue to produce groundbreaking discoveries. By combining its advanced technology with the ingenuity of scientists and engineers around the world, Webb is transforming our understanding of the universe, revealing its complexity, diversity, and beauty. Its observations will continue to shape the fields of astronomy, astrophysics, cosmology, and planetary science, providing answers to long-standing questions while also posing new ones that drive future research. The telescope's mission demonstrates the remarkable achievements possible when scientific ambition, technical innovation, and international collaboration come together in pursuit of knowledge. Webb's ability to capture light that has travelled billions of years allows astronomers to study events and objects from the universe's earliest periods. This includes the formation of the first stars, the assembly of early galaxies, and the chemical enrichment of the cosmos over time. By measuring the redshift of distant galaxies, Webb can determine their distance and age, creating a timeline of cosmic history that extends back nearly 14 billion years. Its infrared instruments are essential for detecting this light, which has been stretched to longer wavelengths by the expansion of the universe. In doing so, Webb provides a window into the earliest phases of galaxy formation, offering insights into the processes that shaped the large-scale structure of the cosmos and the conditions that led to the emergence of stars and planets. The James Webb Space Telescope also provides unparalleled detail in the study of star-forming regions within our own galaxy. By observing molecular clouds, protostars, and young stellar objects, Webb helps astronomers understand the complex processes that govern star formation, including the influence of magnetic fields, turbulence, and radiation. These observations reveal the physical and chemical environments where planets are born, offering clues about how planetary systems like our own solar system form and evolve. Webb can detect protoplanetary disks, measure their composition, and observe how material accretes onto forming planets, shedding light on the earlier stages of planetary evolution and the factors that determine the habitability of worlds. Webb's observations of exoplanets are providing revolutionary insights. Using techniques such as transit spectroscopy, the telescope can detect the chemical fingerprints of molecules in an exoplanet's atmosphere, including water vapor, carbon dioxide, methane, and oxygen. The idea that looking at the sky is also looking back in time is one of the most fascinating and profound discoveries in the history of human understanding of the universe. Light travels at a fixed speed, which we now know as approximately 300,000 kilometers per second, or about 186,000 miles per second. This immense speed is incredibly fast by human standards, but even at this speed, light takes time to move across the vast distances of space. When we see the sun, for example, we are not seeing it as it is right now, but as it was about 8 minutes ago. Its light has travelled the approximately 150 million kilometers from the sun to Earth, taking that small fraction of time to reach our eyes. In the case of the moon, the light takes about 1 second to travel from its surface to our eyes. These times are short, almost negligible to us, but they hint at a much deeper truth when we consider objects that are far beyond our solar system. When we look at the nearest stars, which are light years away, we begin to experience a more dramatic form of looking back in time. A light year is the distance light travels in 1 year, which is nearly 10 trillion kilometers, or about 6 trillion miles. Proxima Centauri, the closest star to our Sun, is about 4.2 light years away. This means that when we observe it, the light we're seeing left that star more than 4 years ago. We are literally observing the past, seeing a star as it was 4 years before this very moment, not as it is at this instant. This principle becomes even more striking as we look at objects thousands, millions, and eventually billions of light years away. When astronomers study galaxies that are millions of light years away, they are not merely observing distant collections of stars, they are looking back in time across millions of years. For instance, the Andromeda Galaxy, the nearest spiral galaxy to the Milky Way, is about 2,500,000 light years away. When astronomers observe it, they are seeing Andromeda as it was 2,500,000 years ago, a time when early humans on Earth were just beginning to develop basic tools and control fire. This extraordinary time gap means that telescopes act as time machines, allowing scientists to reconstruct the history of the universe and understand the development of galaxies over cosmic time. The effect of distance on light observation becomes even more profound when we consider the most distant galaxies ever observed. With advanced space telescopes, especially the James Webb Space Telescope launched in December of 2021, astronomers have been able to observe light that has travelled for more than 13 billion years. This light originated from galaxies that existed less than 1 billion years after the Big Bang, the event that created the universe roughly 13,800,000,000 years ago. The galaxies that Webb has observed are therefore some of the earliest known structures in the cosmos, showing the universe when it was only a fraction of its current age. Observing such ancient light allows scientists to study the conditions of the early universe, the formation of the first galaxies, and the initial clustering of matter that would eventually give rise to stars, planets, and galaxies as we know them today. The process of observing distant light and interpreting it is far from simple. Light carries information not only about the position of an object, but also about its composition, temperature, motion, and other physical properties. When light travels across billions of light years, it is stretched by the expansion of the universe, a phenomenon known as redshift. The more distant a galaxy is, the more its light is shifted toward longer, redder wavelengths. By measuring this redshift, astronomers can calculate how far away a galaxy is and how long its light has been travelling. This technique allows scientists to create a detailed timeline of the universe's history, effectively mapping its evolution from the earliest moments after the Big Bang to the present day. Observing distant light also reveals the life cycles of stars. When astronomers look at a star in a nearby galaxy, they might see it in a stage of life that no longer exists in reality, because the star may have already exhausted its fuel and collapsed into a white dwarf, neutron star, or black hole. This means that every glimpse of light from distant space shows a version of reality that has already changed by the time the light reaches Earth. Some of the stars and galaxies we observe today may no longer exist in the form we see them, but their light preserves a record of their existence, allowing scientists to study processes that are otherwise invisible and inaccessible. The light from very distant objects often takes forms that are invisible to the human eye. The first stars and galaxies emitted light that has been stretched so much that it now appears in the infrared part of the spectrum. The James Webb Space Telescope is designed to detect this infrared light, allowing astronomers to see galaxies that formed more than 13 billion years ago. By capturing this light, scientists can study the earliest structures in the universe, understand how the first stars ignited, and investigate the mechanisms that led to the formation of galaxies. This ability to observe ancient light has transformed our understanding of cosmic history, showing that the early universe was a more active and complex place than previously imagined. When we talk about looking back in time, we're not only considering visual light, but also other forms of electromagnetic radiation. Telescopes can detect X-rays, gamma rays, radio waves, and microwaves, each providing a different view of the universe's past. For example, the cosmic microwave background radiation, first detected in the mid-1960s, is light that has travelled for nearly 13,800,000,000 years. This radiation is a relic of the universe when it was only about 380,000 years old, long before stars or galaxies had formed. By studying this ancient light, scientists have been able to understand the universe's earliest conditions, including its temperature, density, and the distribution of matter at the time. This radiation acts as a snapshot of the universe shortly after its creation, giving a direct glimpse into the conditions that set the stage for all subsequent cosmic evolution. The principle of looking back in time also applies to studying explosive cosmic events such as supernovae. A supernova is a powerful explosion that marks the death of a massive star. When a supernova occurs in a distant galaxy, its light travels across space for millions or even billions of years before reaching Earth. By observing the light from these explosions, astronomers can study the chemical elements produced in the explosion, the processes that lead to stellar death. By observing the light from these explosions, astronomers can study the chemical elements produced in the explosion, the processes that lead to stellar death, and the impact of these explosions on the surrounding galaxy. In some cases, light from supernovae that exploded billions of years ago is only now reaching us, meaning that scientists are witnessing events that happened long before Earth even existed. The concept of looking back in time also helps explain why the night sky appears as it does. The Milky Way, our home galaxy, contains hundreds of billions of stars, each emitting light that has travelled for thousands to tens of thousands of years before reaching us. When we look at distant galaxies through powerful telescopes, we see not just static points of light, but dynamic systems in motion, interacting with one another over millions of years. These observations allow scientists to study galaxy mergers, the growth of supermassive black holes, and the evolution of cosmic structures over time. Each photon of light carries with it a story from the distant past, and by collecting these photons, astronomers can piece together the history of the universe. Even objects within our own solar system contribute to our understanding of time and distance. The light from planets, moons, and asteroids takes minutes to hours to reach Earth, depending on their location. By observing this light, scientists can study the current state of these objects, while also comparing it with earlier data to detect changes over time. For example, studying the light reflected off Mars allows scientists to monitor seasonal changes, dust storms, and surface features, providing a record of the planet's evolving climate and geology. This combination of temporal and spatial observation demonstrates that looking at light is always, in some sense, looking into the past, whether across the solar system or across the universe. The farther we look, the more we confront the scale of cosmic history. When astronomers observe galaxies 10 billion light-years away, they are seeing them as they existed 3,800,000,000 years after the Big Bang, at a time when the universe was only about 27% of its current age. This perspective allows scientists to study the assembly of galaxies, the formation of large-scale structures, and the processes that govern star formation in the young universe. Observing light from different epochs provides a chronological sequence, allowing scientists to reconstruct the universe's development, much like reading the pages of a history book written in light. The challenge of observing distant light lies not only in its faintness, but also in the interference caused by Earth's atmosphere. Many wavelengths of light, especially infrared, cannot penetrate the atmosphere, which is why space telescopes like Hubble and Webb are crucial. Positioned hundreds of kilometers above Earth, these telescopes avoid atmospheric distortion and can capture faint signals that would be impossible to detect from the ground. The James Webb Space Telescope, for example, orbits around the second Lagrange point, located approximately 1,500,000 kilometers from Earth, providing a stable and cold environment ideal for observing ancient light. This location allows Webb to detect the faintest glimmers from the earliest galaxies and study light that has travelled across almost the entire history of the universe. Understanding the concept of looking back in time also requires a grasp of the universe's expansion. The universe has been expanding since the Big Bang, and as space itself stretches, the light travelling through it is stretched as well. This cosmological redshift means that light from the most distant objects is shifted toward longer wavelengths, appearing redder than it originally was. By measuring this redshift, astronomers can determine how fast the universe is expanding and estimate the age of distant galaxies. This technique has provided strong evidence for the universe's growth over billions of years and has helped refine our understanding of cosmic history. Each photon carries not only the image of a distant object, but also a record of the expansion of space itself. The concept of looking back in time has profound implications for understanding the first stars, called population 3 stars. These stars formed from the primordial hydrogen and helium, created in the Big Bang and contained virtually no heavier elements. They ignited hundreds of millions of years after the universe's birth and lived relatively short lives, producing the first heavy elements through nuclear fusion. Observing the light from galaxies that contain remnants of these first stars allows scientists to study the transition from a simple universe dominated by hydrogen and helium to a complex cosmos enriched with elements necessary for planets and life. Each glimpse of these ancient galaxies provides insight into processes that shape the universe's chemical and structural evolution. Observing distant light also informs the study of dark matter and dark energy. These invisible components make up most of the universe's mass-energy content and influence the motion of galaxies, the bending of light, and the universe's expansion rate. By tracing the light from faraway galaxies and measuring how it is distorted by massive objects along its path, astronomers can map the distribution of dark matter. Studying light from galaxies at different distances also helps scientists understand how dark energy has influenced the universe's expansion over time. In this way, light becomes a tool not only for seeing the past, but also for probing the unseen forces that govern cosmic evolution. Gravitational lensing, another phenomenon, further enhances our ability to look back in time. When light from a distant galaxy passes near a massive object such as a galaxy cluster, its path is bent by gravity. This bending magnifies and distorts the light, allowing astronomers to see galaxies that would otherwise be too faint to detect. In some cases, light from galaxies that existed more than 13 billion years ago is amplified through gravitational lensing, providing a rare opportunity to study the universe's earlier structures. These observations reveal details about the formation of stars, the growth of galaxies, and the large-scale structure of the cosmos, offering a window into epochs that would otherwise remain hidden. Looking back in time also helps scientists test theories of cosmic evolution and the Big Bang. By comparing the properties of distant galaxies with those of nearby galaxies, astronomers can study how galaxies grow, merge, and change over billions of years. Observing the distribution of galaxies at different distances allows scientists to trace the development of cosmic structures, measure the rate of star formation across time, and understand how chemical elements are produced and distributed. Light from the distant past serves as a record of these processes, allowing scientists to verify predictions and refine models of the universe's history. Every photon that reaches Earth is a messenger from the past, carrying information across unimaginable distances. The act of observing distant light connects human beings to events that occurred billions of years ago, long before our planet existed. Each observation contributes to a growing understanding of the universe, revealing the interplay between time, space, and matter. This connection transforms our view of reality, showing that the universe is not static, but a dynamic, evolving system with a history that can be read through the light that travels across its vast expanses. The study of distant light also intersects with the search for life beyond Earth. By observing the light from exoplanets orbiting distant stars, scientists can analyze the composition of their atmospheres, searching for chemical signatures that may indicate the presence of life. Light from these distant worlds takes years to centuries to reach Earth, meaning that we are observing these planets as they existed long ago. The ability to detect molecules such as water, oxygen, and methane in these atmospheres allows astronomers to understand the conditions that might support life and compare them with early conditions on Earth. In this sense, looking back in time through light is not only a way to study cosmic history, but also a method for exploring the potential for life across the universe. Even within our galaxy, looking back in time provides insights into the formation of stars and planetary systems. Observations of star-forming regions reveal the processes by which clouds of gas collapse under gravity, ignite nuclear fusion, and form new stars and planetary systems. Some of these regions are thousands of light-years away, so the light we observe shows stages of star formation that may have already evolved or changed. By studying these regions, scientists can understand how stars like the Sun were born, how planets form around them, and how chemical elements are distributed within galaxies. Each observation adds another layer to the story of cosmic evolution, connecting distant events with the history of our own solar system. The concept of looking back in time also influences the way scientists design experiments and interpret observations. Instruments must be sensitive enough to detect faint light that has travelled for billions of years, and data must be carefully analysed to separate ancient signals from noise and interference. Advanced computational models are used to simulate the conditions of the early universe and predict what astronomers should see. Observations are then compared with these models, allowing scientists to refine their understanding of how the universe evolved. Each photon of light becomes a piece of evidence, helping to reconstruct the chronology of cosmic history. Observing the universe in different wavelengths of light further enhances our understanding. Ultraviolet light, for example, reveals regions of intense star formation, while X-rays show the presence of high-energy phenomena such as black holes and neutron stars. Infrared light allows astronomers to see through clouds of dust and observe the earliest galaxies. By combining observations across the electromagnetic spectrum, scientists can build a more complete picture of the universe's past, studying everything from the formation of the first stars to the growth of large-scale structures over billions of years. Each wavelength provides a unique perspective on the past, making the study of distant light a multifaceted and deeply informative endeavour. The ability to look back in time has fundamentally changed our understanding of the universe. We now know that the cosmos is not static but dynamic, evolving over billions of years. Galaxies form, grow, collide, and sometimes disappear, while stars are born, live, and die in cycles that enrich the universe with heavier elements. Observing light from different epochs allows scientists to witness these processes in action, seeing how the universe transforms over time. The past is preserved in the light that reaches us, creating a continuous record of cosmic history that humans can study, interpret, and learn from. From the nearby stars in our own galaxy to the most distant galaxies at the edge of the observable universe, every photon of light represents a journey across space and time. Observing this light allows scientists to construct a timeline of the universe, tracing the development of cosmic structures from the earliest moments after the Big Bang to the present day. This process requires careful observation, precise measurement, and sophisticated analysis, but it reveals an incredible story, that the universe has a history that can be read, understood, and appreciated, all through the light that travels across billions of years and countless kilometers to reach us. When we gaze into the night sky, we are looking at a layered history of light, with nearby stars showing relatively recent events and distant galaxies revealing the ancient past. Every telescope observation contributes to a growing understanding of the universe's timeline, allowing scientists to study the formation of galaxies, the evolution of stars, and the distribution of matter and energy across cosmic history. The concept of looking back in time through light transforms our perception of space, showing that the universe is a vast, dynamic, and ever-changing entity, with a story that unfolds over billions of years. The study of ancient light also informs cosmology, the science of the universe's origin, structure, and evolution. By observing galaxies and cosmic structures at different distances, scientists can test theories of cosmic inflation, the period of rapid expansion that occurred fractions of a second after the Big Bang. They can investigate the formation of the first stars, the growth of supermassive black holes, and the distribution of dark matter. Each photon from distant light becomes a piece of evidence, helping to answer questions about the universe's earliest moments, its large-scale structure, and the physical laws that govern its evolution. In this way, looking back in time is not just an observational tool, but a fundamental approach to understanding the cosmos. As technology advances, the ability to observe distant light continues to improve. New telescopes with larger mirrors, more sensitive detectors, and the ability to operate in multiple wavelengths allow astronomers to see further back than ever before. Each improvement in sensitivity and resolution extends the reach of our cosmic vision, revealing previously hidden galaxies and shedding light on the universe's first billion years. The James Webb Space Telescope, with its ability to detect faint infrared light, has already observed galaxies that existed when the universe was less than 1 billion years old, providing an unprecedented view of the early cosmos. Future missions promise to extend this reach even further, uncovering new details about the universe's history and evolution. The universe began in a state of unimaginable density and heat, a point so small and intense that space itself did not yet exist in any recognizable way. Nearly 14 billion years ago, the event that cosmologists call the Big Bang marked the beginning of the expansion of the universe. At that moment, all the energy and matter that would eventually form stars, galaxies, planets, and life itself was contained in a space smaller than the smallest atom. The laws of physics as we understand them began to take shape, and time itself started to move forward. Immediately after this explosive beginning, the universe was filled with a dense hot plasma made of fundamental particles such as quarks, electrons, and neutrinos. These were the building blocks of matter, but they had not yet combined into the familiar atoms we know today. In the first fraction of a second after the Big Bang, the universe underwent a period of rapid expansion known as cosmic inflation. During this incredibly brief instant, the universe grew exponentially, stretching far beyond its original size. This expansion was not like an explosion into space. Rather, space itself was stretching, carrying everything within it along for the ride. The inflation smoothed out the distribution of energy, and tiny quantum fluctuations were imprinted onto the fabric of space. These fluctuations would later serve as the seeds for the formation of galaxies and large-scale structures. The universe cooled rapidly as it expanded, and within a few seconds the quarks began to combine into protons and neutrons, forming the first atomic nuclei in a process known as nucleosynthesis. During this time, simple elements such as hydrogen, helium, and trace amounts of lithium were created, laying the groundwork for all the chemical elements that would appear later in stars. For the first several 100,000 years, the universe remained a hot, opaque soup of charged particles and radiation. Photons, the particles of light, could not travel freely because they were constantly scattered by electrons. This period is often called the photon epoch, or the era of radiation domination. During this time, the universe continued to expand and cool, and the density of matter gradually became more important than the density of radiation. When the universe was approximately 380,000 years old, it had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This event is known as recombination, and it had a profound effect on the universe because photons were suddenly able to travel freely through space. These ancient photons have been travelling ever since and can still be detected today as the cosmic microwave background radiation, a faint glow that provides a snapshot of the universe at this very early stage. After recombination, the universe entered a period called the Cosmic Dark Ages. There were no stars yet, and the universe was filled mostly with neutral hydrogen and helium gas. During this time, the tiny fluctuations in density left over from inflation began to grow under the influence of gravity. Regions with slightly higher density attracted more matter, becoming gradually denser over time. These overdense regions formed the first large-scale structures in the universe, the precursors of galaxies. Gravity was the key force driving the formation of these structures, pulling matter together to form filaments, clusters, and voids. The universe was still mostly dark, as there were no sources of light except for the faint glow of the cosmic microwave background. As hundreds of millions of years passed, the densest regions of hydrogen and helium gas began to collapse under their own gravity. These clouds of gas became increasingly hot and dense at their centres, eventually igniting nuclear fusion, the process by which hydrogen atoms combine to form helium and release enormous amounts of energy. This marked the birth of the first stars, a time known as the epoch of reionization. These first stars were extremely massive compared to stars like our Sun, sometimes hundreds of times more massive, and they burned their fuel quickly, shining brightly for only a few million years before ending their lives in powerful supernova explosions. The light from these stars began to reionize the surrounding hydrogen gas, transforming the universe from a neutral state back into an ionized state and making it transparent to ultraviolet light. This process gradually ended the cosmic dark ages, filling the universe with light for the first time since the Big Bang. The first stars did not exist in isolation. As they formed, they gathered into the first protogalaxies, small collections of stars held together by gravity. These early galaxies were irregular in shape and much smaller than modern galaxies. Within these galaxies, stars continued to form, live, and die, enriching the surrounding gas with heavier elements created in their cores or during their supernova explosions. Elements such as carbon, oxygen, nitrogen, and iron were produced for the first time, providing the necessary building blocks for planets and eventually life. Gravity continued to drive the growth of structures in the universe, pulling galaxies together into clusters and superclusters, connected by vast filaments of gas and dark matter forming the cosmic web. Dark matter played a crucial role throughout this entire process. Although it does not emit or absorb light, its gravitational influence shaped the formation and evolution of galaxies. Clumps of dark matter acted as gravitational wells, pulling in ordinary matter and helping to organize the cosmic web. The distribution of dark matter determined where galaxies formed and how they clustered together. creating the large-scale structures that astronomers observe today. Without dark matter, the universe would have looked very different, and the first galaxies might have formed much later, if at all. By the time the universe was approximately 1 billion years old, galaxies had begun to take on more recognizable shapes. Spiral and elliptical galaxies emerged as stars continued to form, and as gravitational interactions between galaxies reshaped their structures. Galaxy mergers became common, as smaller galaxies were pulled into larger ones, triggering bursts of star formation and redistributing gas and stars. Supermassive black holes formed at the centers of many galaxies, influencing their evolution through the release of energy in the form of jets and radiation. These black holes grew rapidly by accreting matter from their surroundings, becoming some of the most massive objects in the early universe. Stars themselves evolved in a predictable manner depending on their mass. Low-mass stars, like our Sun, burn their hydrogen fuel slowly and can live for tens of billions of years, while massive stars live fast and die young, exploding as supernovae that spread heavy elements into space. The cycle of star birth, evolution, and death enriched the interstellar medium with elements beyond hydrogen and helium, creating the conditions necessary for the formation of planets and complex molecules. Over time, successive generations of stars formed within galaxies, each generation contributing more heavy elements to the next, gradually building up the chemical complexity of the universe. The formation of the first planetary systems occurred several billion years after the Big Bang. As clouds of gas and dust collapsed around young stars, the dust particles collided and stuck together, forming larger and larger bodies. These bodies eventually grew into planets, moons, asteroids, and comets. The heavier elements required for rocky planets like Earth were created in earlier generations of stars, meaning that planets capable of supporting life could not exist until the universe had undergone several cycles of star formation and supernova enrichment. The first gas giant planets, composed mostly of hydrogen and helium, likely formed earlier, but terrestrial planets with metal-rich cores and rocky surfaces appeared later as the universe became more chemically complex. The assembly of large-scale structures continued alongside the formation of stars and galaxies. Galaxy clusters, massive groups of hundreds or thousands of galaxies bound together by gravity, formed along the filaments of the cosmic web. Superclusters, even larger structures composed of many clusters, became prominent features of the universe on scales of hundreds of millions of light-years. These structures were separated by vast voids, regions of space containing very few galaxies, giving the universe a web-like appearance on its larger scales. Observations of these structures provide insight into the history of the universe, revealing how matter has evolved over billions of years under the influence of gravity, dark matter, and dark energy. The cosmic microwave background, first released nearly 400,000 years after the Big Bang, remained a critical tool for cosmologists studying the early universe. Its uniformity and tiny variations provided evidence for the initial density fluctuations that would later grow into galaxies and clusters. By studying the CMB, scientists could infer the composition of the early universe, the rate of its expansion, and the nature of the first structures. The discovery of the CMB and its detailed measurements by satellites such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and later missions provided a consistent framework for understanding how the universe evolved from a hot, dense plasma to the complex network of stars, galaxies, and clusters observed today. By approximately 3 billion years after the Big Bang, many of the first galaxies had merged to form larger, more stable galaxies, including spirals and ellipticals. Star formation was at its peak during this period, known as cosmic noon, when the universe was a hub of galactic activity. Gas-rich galaxies collided frequently, sparking intense bursts of star formation, and black holes continued to grow at the centers of massive galaxies. The light from these galaxies began to dominate the observable universe, and the large-scale structures were largely in place, although they would continue to evolve for billions of years. Over the next several billion years, star formation gradually slowed as gas reservoirs in galaxies were depleted. Some galaxies became quiescent, containing older stars and little new star formation, while others continued forming stars at reduced rates. The expansion of the universe, driven by dark energy, accelerated over time, causing galaxies to move farther apart and making the universe less dense on large scales. the structure of the universe stabilized into the patterns we observe today, with vast cosmic voids, dense clusters, and interconnected filaments. By the time the universe was approximately 13 billion years old, most galaxies had formed, and the processes of star and planet formation had created a universe filled with the elements necessary for life. Stars continued to form and die, producing supernovae that scattered heavier elements into space, and black holes influenced the evolution of galaxies through energetic feedback. Observations of distant galaxies allow astronomers to look back in time, seeing them as they were billions of years ago, providing a glimpse of the universe during its formative stages. By studying galaxies at different distances, scientists can trace the history of cosmic evolution, observing how matter has coalesced, how structures have grown, and how the chemical composition of the universe has changed over time. Throughout this entire timeline, the expansion of the universe has remained a central feature. Edwin Hubble's observations in the early 20th century showed that galaxies are moving away from each other, indicating that the universe is expanding. This discovery confirmed predictions of the Big Bang theory and provided a framework for understanding the growth of cosmic structures over billions of years. Measurements of the expansion rate, known as the Hubble constant, combined with observations of distant supernovae, have revealed that the expansion of the universe is accelerating, a phenomenon attributed to dark energy, a mysterious component that constitutes the majority of the energy density of the cosmos. Dark energy and dark matter together shape the fate of the universe. Dark matter, invisible but detectable through its gravitational effects, binds galaxies and clusters together, while dark energy drives the accelerated expansion, stretching the fabric of space itself. The interplay between these components determines the large-scale structure and ultimate evolution of the universe, influencing everything from the formation of galaxies to the trajectories of clusters and superclusters. Observations of cosmic structures, gravitational lensing, and the cosmic microwave background provide evidence for the existence and distribution of dark matter and dark energy, allowing scientists to build increasingly detailed models of cosmic evolution. Looking back from the present day, astronomers can piece together a detailed picture of the universe's history, from its earliest moments in the hot, dense state of the Big Bang to the formation of stars, galaxies, and planetary systems. The cosmic timeline illustrates how simple particles combined to form atoms, how these atoms gathered into clouds of gas, how gravity formed the first stars, and how successive generations of stars enriched the universe with the elements necessary for planets and life. The large-scale structures observed today, from galaxy clusters to superclusters, reflect the imprint of initial fluctuations and the influence of dark matter and dark energy, revealing the dynamic processes that have shaped the universe over billions of years. Every observation of distant light allows scientists to look deeper into the past, confirming the general sequence of cosmic events and providing insight into the complex interplay of matter, energy, and fundamental forces that govern the evolution of the cosmos. This timeline, constructed from theoretical models and observations, demonstrates the remarkable journey of the universe from a tiny, hot, dense beginning to the rich and structured cosmos observed today. Stars ignited, galaxies formed and merged, elements built up, and light filled the universe after the Dark Ages. Gravitational forces sculpted the cosmic web, dark matter guided the formation of structures, and dark energy continues to drive the expansion. By following the light from the earliest galaxies to our present-day observations, scientists can reconstruct this story in ever greater detail, revealing the processes that led to the formation of the universe as we know it, and the ongoing evolution of cosmic structures. The universe continues to change and evolve, with stars being born and dying, galaxies merging and growing, and cosmic structures shifting under the influence of gravity. Observations of increasingly distant galaxies allow astronomers to test predictions of cosmological models, understand the role of dark matter and dark energy, and explore the earliest stages of cosmic history. By tracing the light from the first stars and galaxies, scientists are able to confirm the sequence of events that shaped the universe, from the hot beginnings of the Big Bang to the rich tapestry of stars, galaxies, and cosmic structures visible today. Every discovery of an ancient galaxy, every measurement of a distant cosmic microwave photon adds another piece to the puzzle, gradually filling in the full picture of how the universe evolved over nearly 14 billion years, from the first moments of time to the complex and structured cosmos in which galaxies, stars, planets, and life have emerged. The continuous expansion of the universe ensures that its story is far from finished. Galaxies continue to form and evolve, stars continue to shine and die, and matter continues to cluster under the influence of gravity. Dark energy, mysterious and pervasive, drives the acceleration of cosmic expansion, influencing the future distribution of galaxies and the ultimate fate of the universe. Observations of the cosmic microwave background, distant supernova, and large-scale structures provide critical insights into this ongoing evolution, allowing scientists to refine their understanding of the universe's past, present, and future. The cosmic timeline, from the Big Bang through the formation of stars and galaxies, represents a continuous and dynamic history, revealing the intricate processes that have shaped the universe over billions of years and offering a window into the origins of the structures that make up the cosmos today. The formation of stars and galaxies did not happen uniformly across space or time. Different regions of the universe experience slightly different rates of collapse and star formation, leading to the variety of galaxies observed in the modern cosmos. Some regions formed dense clusters of galaxies, while vast voids remained relatively empty. The interplay between gas dynamics, gravity, radiation, and feedback from stars and black holes created a diversity of galactic environments, from dense starburst galaxies to quiet elliptical galaxies dominated by older stellar populations. This diversity continues to be observed and studied by astronomers, providing insight into the complex processes that govern galaxy formation and evolution. The early stars, often called population 3 stars, were composed almost entirely of hydrogen and helium and were critical to the chemical evolution of the universe. Their supernovae seeded the surrounding space with the first heavy elements, enabling the formation of population 2 stars, which contained small amounts of metals. These, in turn, enriched the universe further, leading to the formation of population 1 stars, including stars like the Sun, which contain significant amounts of heavy elements necessary for planets and life. This cycle of star formation and chemical enrichment has continued throughout the history of the universe, creating the conditions necessary for the emergence of planetary systems and biological complexity. Observations of the oldest and most distant galaxies allow astronomers to test theories of star and galaxy formation, revealing that many galaxies formed remarkably quickly after the Big Bang. Some of the earliest galaxies were already massive and luminous when the universe was only a few 100 million years old. This challenges models of galaxy formation, suggesting that processes such as rapid gas, accretion, mergers, and efficient star formation played a significant role in the early assembly of galaxies. These discoveries continue to refine our understanding of the cosmic timeline, showing that the universe's evolution is both rapid and complex, with structures forming earlier and more efficiently than previously anticipated. The combination of observational astronomy, theoretical models, and simulations provides a comprehensive framework for understanding the universe's history. From the initial moments of the Big Bang through the formation of stars and galaxies, cosmologists can trace the evolution of matter and energy, the growth of structure, and the enrichment of the universe with the elements necessary for life. Each generation of stars builds upon the previous one, and each galaxy carries the imprint of its formation history. By studying the cosmic microwave background, distant galaxies, and large-scale structures, scientists continue to reconstruct the universe's timeline with increasing precision, uncovering the processes that shape the cosmos from its earliest moments to the present day. The cosmic timeline also highlights the interplay between fundamental forces and particles. Gravity, electromagnetism, and nuclear forces all influence the formation of stars and galaxies, while dark matter and dark energy govern the large-scale evolution of the universe. The cooling and expansion of the universe set the stage for structure formation, while feedback from stars and black holes regulates star formation and the distribution of gas within galaxies. Observations of these processes across cosmic time provide a detailed picture of how the universe evolved, from the first atoms to the complex galaxies, clusters, and superclusters seen today. By following the light from distant galaxies, astronomers can effectively look back in time, observing the universe as it was billions of years ago. This ability to study ancient light allows scientists to test predictions of cosmological models, observe the formation and evolution of galaxies, and understand the processes that govern star formation and chemical enrichment. The cosmic timeline is a record of these events, showing how the universe has evolved from the initial hot, dense state of the Big Bang to the rich and structured cosmos observed today. Each observation adds a piece to this history, helping to create a coherent picture of cosmic evolution that connects the earliest moments of the universe with the present-day distribution of stars, galaxies, and cosmic structures. The ongoing study of the universe continues to reveal new insights about its formation and evolution. Observations of high-redshift galaxies, ancient quasars, and the cosmic microwave background provide clues about the early universe, while studies of nearby galaxies, star clusters, and interstellar gas inform our understanding of local processes. By combining these observations with simulations and theoretical models, cosmologists can trace the universe's history across billions of years, from the first moments of the Big Bang to the formation of stars and galaxies and beyond. This comprehensive approach allows scientists to reconstruct the cosmic timeline in extraordinary detail, revealing the dynamic processes that have shaped the universe and continue to influence its evolution today. The interplay between stars, galaxies, and cosmic structures demonstrates the complexity of the universe's evolution. Star formation drives the chemical enrichment of galaxies, while galaxy interactions and mergers reshape structures and trigger new generations of stars. Black holes influence their surroundings through energetic feedback, and dark matter provides the gravitational scaffolding that shapes the distribution of matter. Dark energy drives the expansion of space, affecting the separation of galaxies and the growth of large-scale structures. Observing these processes across cosmic time allows scientists to understand how the universe evolved from a simple, hot, dense state to the rich, structured, and dynamic cosmos observed today. The timeline from the Big Bang to the formation of stars and galaxies is marked by a series of interconnected events that transformed the universe. The initial expansion and cooling allowed fundamental particles to form, recombination enabled light to travel freely for the first time, and the resulting cosmic microwave background became a fossil record of the early universe. The subsequent dark ages saw matter clumping under gravity, creating the first dense regions that would eventually collapse into stars and galaxies. The ignition of the first stars brought light back into the universe, ending the dark ages and starting the process of reionization. These stars, massive and short-lived, exploded as supernovae, dispersing heavier elements into the surrounding gas and enriching the universe chemically. Over time, these enriched regions gave rise to the second generation of stars, forming small proto-galaxies, which gradually merged into larger and more complex galaxies. As galaxies grew, they were shaped by both internal processes and external interactions. Gravity pulled stars and gas toward galactic centers, sometimes forming dense bulges, while collisions and mergers with neighboring galaxies could trigger bursts of star formation or create irregular shapes. The development of spiral arms in disk galaxies is driven by density waves that compress gas and trigger ongoing star formation, while elliptical galaxies often result from the mergers of smaller galaxies, containing older stars and less gas for new star formation. These early galactic structures were not static. They evolved as new stars formed, old stars died, and black holes at galactic centers grew and influenced their surroundings through radiation and powerful jets of particles. The chemical evolution of the universe proceeded alongside this structural growth. Each generation of stars produced heavier elements, called metals in astronomy, through nuclear fusion and supernova explosions. Hydrogen and helium, formed in the first minutes of the universe, were gradually supplemented by carbon, oxygen, nitrogen, silicon, and iron. These metals mixed with the surrounding gas, providing the material needed for the formation of rocky planets and complex molecules. The enrichment process was uneven, with some regions of space containing higher concentrations of metals, influencing the types of stars and planets that could form in different parts of the universe. Dark matter continued to play a fundamental role in shaping cosmic structures. Clumps of dark matter formed the gravitational backbone of galaxies and clusters, guiding the accumulation of ordinary matter. Without dark matter, galaxies would not have formed as efficiently or as early as they did. Observations of galaxy rotation curves, gravitational lensing, and the cosmic web all provide evidence of the pervasive influence of dark matter, showing that it outweighs ordinary matter by a factor of approximately 5-1. This invisible component created the gravitational scaffolding necessary for the formation of stars, galaxies, and larger structures, dictating where and how matter clustered throughout cosmic history. By the time the universe was roughly 1 billion years old, galaxy formation had progressed significantly. Galaxies were beginning to merge, forming larger and more complex structures. The first supermassive black holes appeared at the centers of some galaxies, growing rapidly by accreting gas and merging with other black holes. The energy released by these growing black holes, in the form of radiation and powerful jets, influenced star formation within galaxies, sometimes triggering it and other times suppressing it. These feedback processes helped regulate the growth of galaxies, ensuring that star formation did not consume all available gas too quickly, and that galaxies evolved into the diverse types we observe in the modern universe. Star formation rates varied across galaxies, influenced by gas availability, galactic interactions, and feedback from supernovae and black holes. Some galaxies experienced intense bursts of star formation, creating thousands of new stars every year, while others formed stars more slowly, conserving their gas for longer periods. Over time, galaxies depleted their gas reservoirs, and star formation slowed, resulting in populations of older, long-lived stars. The interplay between gas accretion, star formation, and feedback mechanisms created a dynamic balance, shaping the evolution of galaxies over billions of years and determining their structure, composition, and luminosity. By the time the universe was about 3 billion years old, the large-scale structure of the cosmos had become increasingly pronounced. Galaxy clusters, containing hundreds or thousands of galaxies, had formed along filaments of the cosmic web, separated by vast voids with very few galaxies. These structures reflect the initial density fluctuations from the earliest moments of the universe, amplified over billions of years by gravity. Superclusters, massive collections of clusters, emerged as some of the largest known structures in the universe, spanning hundreds of millions of light-years. The formation of these structures demonstrates how tiny initial fluctuations in density could grow into the immense, organized cosmic web observed today. During this period, star formation in galaxies reached its peak, often referred to as cosmic noon. Galaxies were highly active, with gas-rich mergers and interactions driving bursts of star formation. These intense periods of stellar birth produced heavy elements that enriched the interstellar medium, preparing the universe for subsequent generations of stars and the formation of planetary systems. Some of the earliest galaxies had already evolved into well-formed structures with distinct shapes, while others remained irregular, continuing to grow and merge. Observing galaxies at different distances allows scientists to track this evolution, seeing galaxies as they were billions of years ago, and piecing together the timeline of cosmic history. Planet formation followed the chemical enrichment of galaxies. Heavy elements produced in the cores of stars and during supernovae provided the building blocks for rocky planets, moons, asteroids, and comets. Protoplanetary disks formed around young stars, where dust particles collided and coalesced into larger bodies, eventually forming planets. Gas giants formed earlier, primarily from hydrogen and helium, while terrestrial planets formed later as heavier elements became more abundant. The formation of these planetary systems marked a significant milestone in cosmic evolution, as they created the conditions necessary for the potential emergence of life in some regions of the universe. By the present day, roughly 14 billion years after the Big Bang, the universe has evolved into a rich and complex tapestry of galaxies, stars, planets, and large-scale structures. Observations of distant galaxies allow astronomers to look back in time, seeing them as they were when the universe was much younger. These observations reveal that many galaxies formed earlier and more rapidly than previously expected, challenging some models of galaxy formation. The universe's expansion, driven by dark energy, continues to accelerate, causing galaxies to move farther apart and shaping the future evolution of cosmic structures. Despite the vast scales and billions of years involved, the timeline from the Big Bang to the formation of stars and galaxies can be reconstructed through careful observation and theoretical modelling. The ongoing study of the universe's evolution relies on a combination of observational data and theoretical understanding. Telescopes observing different wavelengths of light, from radio waves to gamma rays, allow astronomers to study various stages of star and galaxy formation. Observations of the cosmic microwave background provide insight into the universe's earliest moments, while surveys of nearby and distant galaxies reveal the processes shaping the cosmos over billions of years. Simulations of cosmic evolution, informed by these observations, help scientists understand how matter and energy interact to form stars, galaxies, and larger structures. By combining these approaches, cosmologists can trace the history of the universe from its hot, dense beginning to the complex structures observed today. The diversity of galaxies seen today reflects billions of years of evolution, influenced by star formation, gas dynamics, galactic interactions, and feedback from black holes. Spiral galaxies exhibit ongoing star formation in their disks, while elliptical galaxies contain older stellar populations and little gas. Irregular galaxies retain evidence of past interactions and mergers, while dwarf galaxies are often remnants of larger structures. This variety illustrates the dynamic processes that have shaped the universe over billions of years, from the formation of the first stars and galaxies to the present-day cosmic web. Each galaxy carries a record of its formation and evolution, providing clues to the broader history of the universe. The formation of stars and galaxies is intimately connected to the distribution of matter and energy in the universe. Gravity drives the collapse of gas clouds to form stars, while dark matter structures guide the formation of galaxies. Feedback from supernovae and black holes regulates star formation, influencing the chemical composition and evolution of galaxies. Dark energy accelerates cosmic expansion, affecting the separation of galaxies and the growth of large-scale structures. Observing these processes across cosmic time allows scientists to reconstruct the universe's timeline, revealing how the initial conditions of the Big Bang led to the complex and structured cosmos observed today. The first generations of stars set the stage for all subsequent cosmic evolution. Their formation, life cycles, and deaths enrich the universe with heavy elements, enabling the formation of more complex stars, planetary systems, and ultimately the conditions for life. The earliest galaxies, though small and irregular, merged and evolved into the larger and more organized galaxies seen today. Clusters and superclusters formed along the cosmic web, reflecting the influence of gravity and dark matter on large scales. This sequence of events, from the first atoms to the formation of stars and galaxies, illustrates the interconnected processes that shape the universe over billions of years. Observations of distant galaxies continue to refine our understanding of cosmic history. Some galaxies appear surprisingly massive at very early times, suggesting that star formation and galaxy assembly occurred rapidly in the young universe. Others provide evidence of the chemical enrichment process, showing how elements produced in earlier generations of stars spread through the interstellar medium. By studying these galaxies, astronomers can test theoretical models, understand the timing and mechanisms of star formation, and explore the role of dark matter and dark energy in shaping the cosmos. Each new observation adds to the detailed timeline of the universe, revealing the processes that led from the Big Bang to the formation of stars and galaxies. The cosmic timeline demonstrates the dynamic and evolving nature of the universe. From the initial hot, dense state, matter coalesced under gravity, forming the first stars and galaxies. Subsequent generations of stars enriched the universe chemically, while dark matter and dark energy shaped the growth and distribution of structures. The interplay of these forces and processes over billions of years produced the rich and structured universe observed today. By studying both nearby and distant galaxies, as well as the cosmic microwave background, scientists continue to reconstruct the sequence of events that transformed the early universe into a complex cosmic landscape filled with stars, galaxies, and the potential for life. The study of the universe's evolution highlights the importance of timescales that span billions of years. Processes such as star formation, supernova explosions, galaxy mergers, and the growth of black holes occur over millions to billions of years, gradually shaping the cosmos. Observing ancient light allows astronomers to look back in time, revealing how galaxies formed and evolved. The combination of observational astronomy, theoretical modelling, and simulations provides a comprehensive picture of the cosmic timeline, illustrating the sequence of events from the Big Bang to the formation of stars and galaxies, and demonstrating how the universe has grown increasingly complex over its nearly 14 billion year history. The universe's evolution continues to be an active field of study. New telescopes and observational technologies allow scientists to detect fainter and more distant galaxies, pushing the observable timeline closer to the moment of the Big Bang. These observations provide critical data on the earliest phases of star formation, galaxy assembly, and chemical enrichment, By examining these ancient objects, astronomers can test and refine models of cosmic evolution, gaining insight into the processes that shape the universe from its earliest moments to the present day. The timeline from the Big Bang to the formation of stars and galaxies remains a foundational framework for understanding the cosmos, linking the universe's hot, dense beginnings to the rich structures and diverse populations of stars and galaxies observed today. The interplay of forces, matter, and energy throughout cosmic history illustrates the complexity of the universe's evolution. Gravity shaped the collapse of gas clouds and the formation of galaxies. Dark matter provided the scaffolding for large-scale structures, and dark energy drives the ongoing expansion of space. Stars, through nuclear fusion and supernova explosions, produced the heavy elements necessary for planets and life. Black holes influence galactic evolution through feedback processes, while galactic mergers and interactions redistributed stars and gas, creating the diversity of galaxies observed today. Each stage in this cosmic timeline contributed to the universe's transformation from a simple, hot, dense state into the structured and chemically rich cosmos of the present. The study of distant galaxies allows astronomers to trace the universe's history with remarkable precision. By measuring the redshift of light from galaxies billions of light years away, scientists can determine how far back in time they are observing. This enables a direct glimpse into the early stages of galaxy formation and star formation, revealing how the first cosmic structures grew and evolved. Observations of ancient galaxies show that star formation and chemical enrichment proceeded rapidly in some regions, while other regions evolved more slowly. The resulting diversity of galaxies provides insight into the processes that have shaped the universe over billions of years, from the first stars and proto-galaxies to the mature galaxies seen today. The cosmic timeline from the Big Bang to the formation of stars and galaxies encompasses an incredible sequence of events. From the initial hot, dense state, the universe expanded and cooled, allowing fundamental particles to form and eventually combine into atoms. These atoms clustered under gravity, forming the first stars which ignited and ended the cosmic dark ages. Successive generations of stars enriched the universe chemically, while galaxies formed, merged, and evolved into the diverse structures observed today. Dark matter guided the assembly of large-scale structures, and dark energy drives the universe's accelerated expansion. Observations of distant light provide a window into this history, allowing scientists to reconstruct the universe's timeline and understand the processes that have shaped the cosmos over nearly 14 billion years. The first galaxies were small and irregular, but as star formation continued, mergers and accretion of gas created larger and more structured galaxies. Elliptical galaxies emerged from collisions and mergers, while spiral galaxies developed disks and arms due to rotational dynamics and density waves. Dwarf galaxies, often satellites of larger galaxies, provide insight into the processes of galaxy formation and the influence of dark matter. The interplay between gas dynamics, star formation, feedback processes, and gravitational interactions shaped the evolution of these galaxies, producing the diversity of galactic forms observed in the universe today. Stars themselves evolved in ways that influenced the broader universe. Massive stars, short-lived and luminous, produced heavy elements through nuclear fusion and supernova explosions, while low-mass stars burned their fuel slowly, providing long-lived sources of light and energy. The balance between these different stellar populations affected the chemical composition of galaxies, the formation of planetary systems, and the enrichment of the interstellar medium. Over billions of years, successive generations of stars transformed the universe from a simple mixture of hydrogen and helium into a chemically complex environment capable of supporting planets and, eventually, life. The continuous expansion of the universe, along with the formation and evolution of stars and galaxies, demonstrates the dynamic and ongoing nature of cosmic history. Dark energy, driving the accelerated expansion of space, influences the separation of galaxies and the evolution of large-scale structures. Gravity, dark matter, and the energy produced by stars and black holes interact to shape galaxies and clusters, creating the cosmic web. Observing distant galaxies allows astronomers to look back in time, tracing the evolution of stars, galaxies, and large-scale structures over billions of years. This timeline provides a comprehensive view of how the universe evolved from its earliest moments to the structured cosmos observed today. The formation of stars and galaxies represents a crucial stage in cosmic evolution. Stars produced the elements necessary for planets, while galaxies served as the environments where these stars formed and evolved. Large-scale structures, shaped by dark matter and gravity, provided the framework for the distribution of galaxies. Observations of the cosmic microwave background, distant galaxies, and supernovae allow scientists to reconstruct the universe's history, providing a detailed timeline from the Big Bang to the emergence of stars and galaxies. Each discovery, from the oldest star to the most distant galaxy, adds to our understanding of how the universe transformed over nearly 14 billion years. The processes that led from the first atoms to the formation of stars and galaxies are interconnected and complex. Gravity caused matter to clump, leading to the collapse of gas clouds and the ignition of the first stars. Supernovae enriched the surrounding medium, enabling the formation of later generations of stars and planets. Galaxy mergers reshaped structures and triggered new star formation, while dark matter guided the assembly of cosmic structures. Dark energy drives the universe's expansion, influencing the evolution of large-scale structures. Together, these processes created the rich and complex universe observed today, providing a record of cosmic history that extends from the Big Bang to the present day. The timeline of the universe from the Big Bang to the formation of stars and galaxies illustrates the interplay of fundamental forces, matter and energy over billions of years. From the initial expansion and cooling to the ignition of the first stars, the enrichment of the universe, and the assembly of galaxies, each stage is connected to the next. Observations of distant light allow scientists to look back in time, reconstructing the sequence of events that shape the cosmos. The evolution of stars, galaxies, and large-scale structures demonstrates the dynamic nature of the universe, revealing how simple beginnings gave rise to the complex and structured cosmos observed today. The first galaxies not only produced stars but also became the birthplaces of planetary systems. Heavy elements created in stars and dispersed by supernovae formed the material for rocky planets and moons. Over time, gas and dust coalesced in protoplanetary disks around young stars, forming planets of varying sizes and compositions. Gas giants formed primarily from hydrogen and helium, while terrestrial planets formed from heavier elements. This process connected stellar evolution to planetary formation, linking the cosmic timeline of star formation to the emergence of planetary systems capable of supporting life. The formation of large-scale structures continued alongside the evolution of stars and galaxies. Filaments, clusters, and superclusters formed along the cosmic web, shaped by the distribution of dark matter and the influence of gravity. Voids, vast regions with few galaxies, developed between these dense structures, creating the large-scale patterns observed in the universe today. Studying these structures provides insight into the growth of cosmic matter, the role of dark matter, and the effects of dark energy on the evolution of the universe. The study of distant galaxies, cosmic microwave background radiation, and large-scale structures provides a detailed picture of the universe's evolution. Observations reveal how stars and galaxies formed, merged, and evolved, and how the universe became chemically enriched. The timeline from the Big Bang to the formation of stars and galaxies shows the sequence of events that transformed the universe from a hot, dense state into the structured and chemically complex cosmos observed today. Each observation adds to our understanding, allowing scientists to trace the history of cosmic evolution over nearly 14 billion years. This history of the universe demonstrates that the formation of stars and galaxies is a central chapter in cosmic evolution. Gravity, dark matter, and dark energy shaped the distribution of matter, while stars produced the elements necessary for planets and life. Galaxies evolved through mergers, interactions, and internal processes, creating the diversity observed today. Observing the universe at different stages allows astronomers to reconstruct its timeline, understanding how the early universe transformed into a complex structured cosmos filled with stars, galaxies, and planetary systems. The process of star and galaxy formation continues to influence the universe today. New stars are still forming in gas-rich regions of galaxies, while old stars die, contributing their material to the interstellar medium. Galaxies continue to merge and interact, reshaping their structures and triggering new star formation. Dark energy drives the expansion of the universe, affecting the growth and separation of large-scale structures. Observations of these ongoing processes along with light from distant galaxies, allow scientists to understand both the past and present evolution of the universe, providing a detailed view of how stars and galaxies formed and evolved over billions of years. Light in the universe behaves in ways that are both predictable and extraordinary, and one of the most fascinating behaviours it exhibits is known as redshift. When we look out into space, the light that reaches us from distant objects, such as stars, galaxies, and quasars, does not always retain the same characteristics it had when it was first emitted. Instead, as it travels across the vast stretches of the cosmos, this light can change in a way that tells us vital information about the universe, including the distances of cosmic objects and the time that has passed since the light began its journey. Redshift is one of the most essential tools astronomers use to understand the size, structure, and history of the universe. Redshift occurs when the wavelength of light stretches, making it appear longer than it originally was. Light consists of electromagnetic waves, and these waves have a characteristic length called the wavelength. Wavelength determines the colour of the light, with shorter wavelengths corresponding to blue light and longer wavelengths corresponding to red light. When an object in space is moving away from us, the light it emits is stretched into longer wavelengths, shifting it toward the red part of the spectrum. This phenomenon is directly related to the motion of the object relative to us, and it was first observed in the early 20th century, profoundly influencing our understanding of the cosmos. Edwin Hubble, an American astronomer, played a central role in connecting redshift to the expanding universe. In the 1920s, he observed that galaxies appeared to be moving away from us, and that their recessional speed was proportional to their distance. In other words, the farther away a galaxy was, the faster it seemed to be moving away. This relationship, now known as Hubble's law, provided the first solid evidence that the universe itself is expanding, and it transformed the study of cosmology. By measuring the redshift of light from distant galaxies, astronomers can determine not only the speed at which these galaxies are moving away, but also how far away they are, since the universe has been expanding steadily over time. The stretching of light is not limited to just the red part of the spectrum. It applies to all forms of electromagnetic radiation, from ultraviolet light to infrared, and even radio waves. This makes redshift a universal tool, allowing scientists to study objects at distances that were once unimaginable. The further away a galaxy or quasar is, the more its light has been stretched by the expansion of space itself. For galaxies that are only a few million light-years away, the shift is relatively small, but for galaxies billions of light-years distant, the stretching is immense. Light from some of the earliest galaxies, formed less than 1 billion years after the universe began, has been stretched so dramatically that it now appears in the infrared part of the spectrum, completely invisible to the human eye without the aid of specialized instruments like the James Webb Space Telescope. Redshift is quantified using a dimensionless number called Z, which represents the ratio of the change in wavelength to the original wavelength. A redshift of 0 means that the light has not been stretched at all, while higher values of Z indicate greater stretching and therefore greater distance. For example, a galaxy with a redshift of 1 has light that has doubled in wavelength since it was emitted. A galaxy with a redshift of 7 has light that has been stretched 8 times its original wavelength. Measuring these redshifts allows astronomers to construct a map of the universe, showing where galaxies are located in both space and time. The relationship between redshift and distance is complex because it involves both the motion of objects and the expansion of space itself. There are 3 main types of redshift that scientists consider: Doppler redshift, gravitational redshift, and cosmological redshift. Doppler redshift occurs due to the motion of an object relative to the observer, similar to the change in pitch of a passing siren that causes a sound to stretch or compress. Gravitational redshift is a result of light losing energy as it escapes the gravitational pull of a massive object, causing the wavelength to lengthen. Cosmological redshift, which is most relevant for understanding the large-scale structure of the universe, arises because the fabric of space itself is expanding, stretching the light as it travels over vast distances. While Doppler and gravitational redshifts occur locally, cosmological redshift dominates the light coming from the most distant galaxies. Redshift not only tells us about distance, but also reveals the age of the universe at the time the light was emitted. Since light travels at a finite speed of approximately 300,000 kilometers per second, when we observe a galaxy 10 billion light-years away, we are seeing it as it was 10 billion years ago. By measuring the redshift of such distant galaxies, astronomers can calculate how much the universe has expanded since that light left its source. This gives a direct glimpse into the conditions of the early universe, helping to answer questions about galaxy formation, star formation, and the evolution of cosmic structures over billions of years. Observing redshift requires extremely precise instruments. Light from distant galaxies is often incredibly faint, having travelled billions of light years, losing intensity as it spreads out across the vast emptiness of space. Telescopes equipped with spectrographs can split light into its component wavelengths, revealing subtle shifts that indicate redshift. Spectra contain dark absorption lines, caused by elements such as hydrogen, helium, and heavier elements absorbing light at specific wavelengths. By comparing the observed positions of these lines with their known laboratory values, astronomers can calculate the exact amount of redshift. This process requires careful calibration and correction for factors like the motion of Earth and the distortion caused by interstellar dust, but it provides one of the most accurate ways to measure cosmic distances. The discovery of highly redshifted galaxies has challenged our understanding of the early universe. The James Webb Space Telescope, launched on December 25, 2021, has been particularly instrumental in this regard. It observes primarily in the infrared, allowing it to detect light from the first galaxies that formed only a few 100 million years after the Big Bang. Some of these galaxies exhibit redshifts of 10 or more, meaning their light has been stretched more than 11 times its original wavelength. This allows astronomers to study not only the distance and age of these galaxies, but also their composition, structure, and star-forming activity during the universe's earliest epochs. The discoveries of Webb have revealed galaxies that appear surprisingly massive and well-formed at such early times, raising questions about how quickly galaxies could assemble and challenging existing models of cosmic evolution. Redshift also plays a crucial role in measuring the expansion rate of the universe, often described by the Hubble constant. By observing supernovae, which are exploding stars of known intrinsic brightness, in distant galaxies, scientists can determine their distances independently of redshift. Comparing these distances with redshift measurements provides a direct calculation of the Hubble constant. Surprisingly, different methods of measuring the Hubble constant have yielded slightly different values, leading to the so-called Hubble tension. This discrepancy is one of the most pressing puzzles in modern cosmology, and it may hint at new physics beyond the standard model of cosmology. The concept of redshift extends even to the cosmic microwave background, the faint afterglow of the Big Bang. This radiation, emitted nearly 13,800 billion years ago, was originally in the form of high-energy light, but it has been redshifted into the microwave range due to the expansion of the universe. Measuring the redshift and temperature of this background radiation provides a snapshot of the universe when it was only about 300,000 years old. Variations in the redshifted cosmic microwave background reveal tiny density fluctuations that would later grow into galaxies and clusters, offering a remarkable view of the universe in its infancy. Beyond galaxies, redshift helps study quasars, which are extremely bright and distant objects powered by supermassive black holes. Quasars often have redshifts greater than 6 or 7, meaning their light has travelled for more than 12 billion years before reaching Earth. The spectral lines of quasars provide information about both the quasars themselves and the intergalactic medium through which their light has passed. By analysing redshifted absorption lines, astronomers can trace the distribution of hydrogen gas in the early universe, revealing how the first cosmic structures influenced their surroundings. Redshift also offers insights into the motion of galaxies within clusters. Galaxies are not just moving away due to cosmic expansion, they also orbit the centre of mass of their clusters. By measuring small variations in redshift, astronomers can determine the velocities of individual galaxies and infer the total mass of the cluster, including the unseen contribution of dark matter. This technique has been vital for understanding that most of the mass in the universe is not visible, and that dark matter dominates the gravitational landscape of cosmic structures. Light stretching, or redshift, also has implications for future observations. As astronomers push to detect objects at ever higher redshifts, they probe closer to the epoch of reionization, a period when the first stars and galaxies ionized the neutral hydrogen that filled the universe. Observing this epoch requires extreme sensitivity to faint, highly redshifted light. Instruments like Webb and future telescopes, including next-generation ground-based observatories, are designed to capture this light, opening a window into the transition from a simple dark universe to the complex structured cosmos we see today. In addition, redshift helps determine the chemical evolution of the universe. By analysing the spectral lines of highly redshifted galaxies and quasars, astronomers can measure the abundance of elements formed in the first generations of stars. These measurements indicate how quickly stars produced heavier elements and how early galaxies enriched their environments with the building blocks for planets and life. Light stretching, therefore, serves not only as a ruler for distance and time, but also as a probe into the chemical history of the cosmos. Redshift is deeply connected to the geometry of space and the overall fate of the universe. Observations of distant supernovae, combined with redshift measurements, have revealed that the expansion of the universe is accelerating, a discovery that led to the concept of dark energy. The precise way in which light from distant objects is redshifted informs models of cosmic expansion, helping to constrain the amount and nature of dark energy. Studying the stretching of light across billions of light years allows scientists to test different scenarios for the ultimate destiny of the universe, from endless expansion to potential future contraction. The use of redshift has grown increasingly sophisticated with modern technology. Large-scale surveys such as the Sloan Digital Sky Survey have measured the redshifts of millions of galaxies, creating a three-dimensional map of the local universe. These maps reveal the large-scale structure of the cosmos, including the vast filaments, walls, and voids formed by the gravitational interaction of galaxies over billions of years. Redshift allows astronomers to reconstruct the cosmic web, providing context for galaxy formation and evolution within the grand structure of space. Redshift measurements also provide checks on fundamental physics. The constancy of physical constants over cosmic time can be tested by observing spectral lines at different redshifts. If the fine structure constant or the electron-to-proton mass ratio had changed significantly, it would leave a measurable imprint in the redshifted spectra of distant galaxies and quasars. So far, observations suggest remarkable stability, confirming that the laws of physics have remained consistent across much of the universe's history. Even within our own Milky Way, redshift helps astronomers measure motion and rotation. The Doppler effect produces both redshift and blueshift, depending on whether stars or gas clouds are moving away or toward us. By carefully mapping these shifts across the galaxy, scientists can trace spiral arms, measure rotational speeds, and estimate the distribution of mass, including dark matter. Redshift is therefore a versatile tool, applicable from local star clusters to the edge of the observable universe. Light stretching has profound implications for time in the universe. A phenomenon called time dilation occurs in conjunction with redshift. When we observe distant events, such as supernova explosions in faraway galaxies, their apparent duration is longer than it would be locally. This happens because the expansion of space stretches not only the wavelength of light, but also the intervals between the arrival of photons. Observing time dilation provides another test of cosmological models and confirms predictions based on the stretching of light across billions of years. Redshift also allows astronomers to refine estimates of the age of the universe. By combining the redshift of the most distant galaxies and quasars with models of cosmic expansion, scientists can determine how long it has been since the Big Bang. Observations indicate that the universe is approximately 13,800 million years old, with some uncertainty of a few tens of millions of years. This measurement relies fundamentally on understanding how light stretches over cosmic distances, demonstrating the central role of redshift in modern cosmology. In recent years, the detection of extremely high redshift galaxies has sparked debates about the early growth of structure in the universe. Some galaxies observed by Webb appear too massive or too evolved for the time at which we see them, raising questions about how quickly matter could have collapsed under gravity to form stars and galaxies. These findings suggest that our models of cosmic evolution may need refinement, and that redshift is not just a measurement tool but also a guide to the limits of our theoretical understanding. Redshift also connects to the study of gravitational lensing, where the light from a distant galaxy is bent by the gravity of a massive object in the foreground. The stretching of light in such cases is a combination of cosmic expansion and the lensing effect, providing information about both the distant source and the intervening mass. This allows astronomers to study dark matter distribution, galaxy mass profiles, and the geometry of space in unprecedented detail. Beyond astronomy, redshift has philosophical implications. By observing light that has travelled for billions of years, we are literally seeing the universe as it was long before the formation of our solar system, our planet, or humanity itself. The stretching of light connects the present moment with the distant past, making redshift a bridge across time and space, a tool that allows us to explore history on a cosmic scale. Technology continues to enhance our ability to measure redshift with precision. Adaptive optics, space-based telescopes, and advanced spectrographs reduce noise and correct for distortions, enabling the study of fainter and more distant objects. Large telescopes on Earth, such as those with mirrors 10 meters or more in diameter, can gather enough light to detect tiny spectral shifts, while space telescopes avoid atmospheric interference entirely, capturing the faintest glimmers from the edge of the observable universe. Redshift is not a static concept, but an evolving field. As new instruments come online and new surveys map more of the cosmos, the data from redshift measurements become increasingly refined. This allows for more detailed models of cosmic expansion, galaxy formation, and the distribution of matter and energy throughout the universe. By observing how light stretches over billions of years, astronomers gain insights not only into where the universe has been, but also into where it might be going. In the context of cosmic history, redshift is a clock and a ruler. It measures distance, time, velocity, and expansion simultaneously, linking the observable properties of light to the dynamics of the universe. Without redshift, our understanding of galaxies billions of light-years away would be limited to their apparent brightness, offering no information about when or how they formed. Redshift transforms these faint specks of light into a narrative of cosmic evolution, revealing the interplay between matter, energy, and the fabric of space itself. As a final note, redshift continues to challenge and inspire astronomers. Every new observation of a highly redshifted galaxy or quasar provides a test for cosmological models, pushing the limits of our understanding. The phenomenon connects the local universe with the farthest reaches of space, the present with the past, and theory with observation. By studying the stretching of a light, we not only measure distances and ages, but also explore the underlying principles that govern the cosmos, making redshift an indispensable window into the universe's past, present, and future. The cumulative effect of studying redshift over decades has been profound. It has transformed cosmology from a field concerned mainly with the local universe into one capable of exploring the very first moments of cosmic history. Redshift has allowed astronomers to map the expansion of space, measure the ages of stars and galaxies, detect the presence of dark matter and dark energy, and understand the large-scale structure of the universe. Every new measurement adds another piece to the puzzle, revealing the complexity and richness of a cosmos that continues to expand, evolve, and surprise those who observe it with careful attention and curiosity. The beauty of redshift lies in its simplicity and universality. It is a single measurable effect that arises naturally from the behavior of light and the expansion of space. Yet from this simple effect, a wealth of information flows, offering insights into distances, ages, velocities, masses, chemical compositions, and the very dynamics of the universe. By observing the stretching of light, humanity has gained a profound connection to the cosmos, bridging billions of light years and billions of years of time. Through redshift, the universe becomes a readable story. Every spectral line shifted toward the red end of the spectrum tells a tale of motion, distance, and the passage of time. From nearby stars to the most distant quasars, from the cosmic microwave background to the earliest galaxies, redshift provides a consistent framework for interpreting the light that reaches our telescopes. It allows scientists to place objects in space and time, revealing the interconnectedness of all cosmic structures across vast scales. Redshift also opens doors to future discoveries. As telescopes improve and observations extend deeper into the infrared, astronomers anticipate finding galaxies at redshifts exceeding 15, corresponding to times less than 300 million years after the universe began. Such observations will probe the very dawn of galaxy formation, the birth of the first stars, and the initial stages of cosmic chemical evolution. Light that has travelled for nearly the entire age of the universe carries the fingerprints of these earliest events, and redshift is the key that unlocks their meaning. Even the study of exoplanets can benefit from redshift, particularly when observing the motion of stars in other galaxies, or detecting the subtle gravitational effects that distant massive objects exert on light. precise measurement of redshifted spectra allows scientists to detect motion, composition, and sometimes even the presence of planets around stars in distant systems. While this application is less common than galaxy observations, it highlights the versatility of redshift as a tool across different scales of astronomy. Redshift reinforces the profound interconnectedness of the universe. The light we observe today has travelled for billions of years, carrying information about events that occurred long before the Earth existed. Every galaxy, star, and quasar we observe has its own redshift, its own story of motion and evolution, yet all are linked through the expansion of space. By measuring redshift, scientists can place each object within the larger cosmic framework, constructing a coherent picture of the universe that spans both space and time. Redshift also plays a vital role in testing new theories of physics. Modified gravity models, alternatives to dark energy, and theories of cosmic inflation all predict subtle differences in how light should be stretched over vast distances. By comparing predicted redshifts with observed values, astronomers can confirm or challenge these models, refining our understanding of the fundamental laws that govern the cosmos. The stretching of light thus serves as both a ruler and a probe for the deepest questions in science. The universe, vast and intricate, stretches far beyond the reaches of ordinary human experience, and its story is written in the light that travels across unimaginable distances. Galaxies, those massive collections of stars, gas, dust, and dark matter, serve as cosmic time capsules, carrying within them the record of the universe's early days. By studying them, scientists can understand how the cosmos evolved from a hot, dense state nearly 14 billion years ago into the richly structured tapestry we observe today. One of the most startling revelations in modern astronomy comes from the discovery of galaxies that seem far older than what prevailing cosmological theories would predict, based on their redshift, a measure of how much the universe has expanded since the light left them. These galaxies challenge conventional ideas about how quickly stars and galaxies could form and evolve in the early universe. Redshift is a cornerstone in understanding cosmic history. As light travels through the expanding universe, its wavelength stretches, shifting toward the red part of the spectrum. This stretching is directly related to how far away the source of the light is, and by extension, how long ago that light was emitted. A higher redshift means the light has been travelling for a longer time, and that we are observing the object as it existed further back in time. By measuring redshift, astronomers can construct a timeline of the universe, identifying when stars first ignited, when galaxies coalesced, and when the cosmic web of matter began to take shape. It is through this lens of redshift that the unexpectedly ancient galaxies were first identified. Observations made by the James Webb Space Telescope, humanity's most powerful instrument for peering into the distant universe, have brought these surprising galaxies into focus. Launched in the year 2021, the telescope was designed to capture infrared light, allowing it to see through cosmic dust and observe objects that formed mere hundreds of millions of years after the universe began. Infrared light is crucial because the expansion of space stretches the light from distant galaxies into longer wavelengths. The telescope's sensitivity revealed galaxies at redshifts corresponding to times less than a few hundred million years after the Big Bang, yet these galaxies displayed properties typical of systems that had already undergone extensive evolution. For example, many of these galaxies exhibited a level of chemical enrichment and stellar maturity that was unexpected. In simpler terms, their stars had already produced heavier elements such as carbon, oxygen, and iron through nuclear fusion and supernova explosions, indicating multiple generations of star formation. According to standard cosmology, the earliest galaxies should have been composed almost entirely of hydrogen and helium, the simplest elements formed during the first few minutes of the universe's existence. The presence of significant amounts of heavier elements in galaxies observed less than 1 billion years after the Big Bang implies that star formation and supernova activity must have been extremely rapid, far faster than previously thought. Another intriguing aspect of these galaxies is their size and mass. Some of the unexpectedly ancient galaxies observed by Webb appear to be surprisingly massive, containing hundreds of billions of stars, comparable to the Milky Way in the present-day universe. According to conventional models, such large structures should have required much more time to assemble through the gradual accumulation of smaller galaxies and gas clouds. Their existence at such early times suggests that processes of galaxy formation in the young universe may have been more efficient, or that our understanding of the timeline of cosmic growth is incomplete. The light from these galaxies also provides insights into their age and star formation history. By analysing the spectrum of light, astronomers can determine the ages of the stars within a galaxy. Many of the newly discovered ancient galaxies show evidence of stars that are already several hundred million years old, even though the universe itself was only a few hundred million years past its beginning. This raises profound questions about the speed at which the first stars and galaxies could have formed. It also forces scientists to reconsider the models of how matter clumped together under the influence of gravity, how the first stars ignited, and how early galaxies evolved into the complex systems we see today. These discoveries have sparked a wave of excitement and debate within the scientific community. The unexpectedly ancient galaxies challenge the assumptions embedded in the widely accepted lambda cold dark matter model, the framework that describes the universe's expansion and the formation of large-scale structures. While this model has successfully explained many observations, such as the cosmic microwave background radiation and the distribution of galaxies on large scales, the presence of these mature galaxies so early in cosmic history suggests that some aspects of the model may need revision. Perhaps the processes of star formation were more efficient, or there were mechanisms that allowed matter to collapse into galaxies more quickly than previously understood. The implications of these findings extend beyond the study of galaxies themselves. Understanding the timing and pace of galaxy formation affects our knowledge of cosmic reionization, a phase in which the first stars and galaxies ionized the neutral hydrogen that filled the universe after the Big Bang. Reionization marks a critical transition in the universe, ending the so-called cosmic dark ages and making the universe transparent to ultraviolet light. If galaxies formed earlier and evolved more quickly than expected, this would shift the timeline of reionization, suggesting that the universe became transparent to light sooner than current models predict. Observations of these ancient galaxies also provide a window into the early environments in which stars formed. By examining the distribution of elements and the properties of the interstellar medium within these galaxies, astronomers can infer the physical conditions that allowed rapid star formation. Some galaxies show high rates of star formation, producing hundreds of solar masses of stars each year, while others appear more quiescent, suggesting a diversity of early galactic environments. Understanding this diversity is essential for building accurate models of galaxy evolution, and for interpreting the cosmic history recorded in the light that reaches Earth today. These galaxies also raise intriguing questions about dark matter, the mysterious substance that constitutes roughly 85% of the universe's total mass but does not emit light. Dark matter plays a critical role in galaxy formation, providing the gravitational scaffolding around which visible matter can accumulate. If galaxies formed and evolved more quickly than expected, this may imply that our understanding of how dark matter interacts with ordinary matter, or the properties of dark matter itself, needs to be revisited. Some theories suggest that dark matter could have been more clumpy, or that interactions between dark matter particles influenced the pace of early galaxy formation. Another layer of complexity comes from the potential presence of supermassive black holes within these ancient galaxies. Observations have revealed that even in the very early universe, some galaxies host black holes with masses of hundreds of millions, or even billions of times the mass of the Sun. The formation of such massive black holes in a relatively short period is difficult to explain under standard scenarios. If the galaxies themselves were already mature and massive, their central black holes could have grown in tandem, suggesting that the co-evolution of galaxies and black holes was already well underway at a time when the universe was only a fraction of its current age. The discovery of these ancient galaxies also provides an important calibration point for theoretical models and computer simulations of the early universe. Cosmological simulations attempt to recreate the formation of galaxies and large-scale structures by inputting known physical laws and initial conditions from the Big Bang. The presence of mature galaxies at early times serves as a crucial test for these simulations, highlighting where models succeed and where they fall short. Some simulations struggle to produce galaxies of comparable mass and maturity within the first few 100 million years, while others require adjustments to star formation rates, feedback processes, or assumptions about dark matter properties to match observations. Furthermore, studying these galaxies offers a direct glimpse into the diversity of galactic forms in the young universe. While some ancient galaxies appear relatively smooth and compact, others display irregular shapes, clumps, or signs of interactions with neighbouring galaxies. These morphological features inform astronomers about the processes shaping galaxies, such as mergers, tidal interactions, and internal star-forming activity. Observing these structures so early in cosmic history suggests that complex dynamics were already influencing galaxy evolution from the outset. The chemical composition of these galaxies provides a record of early nucleosynthesis, the formation of elements within stars. Spectroscopic measurements reveal ratios of elements that indicate multiple generations of stellar evolution, with older stars enriching the interstellar medium and subsequent generations forming from this enriched material. The presence of such chemical maturity at unexpectedly early times implies a rapid cycle of star birth, evolution, and death, compressing what was thought to be a gradual process into a far shorter timescale. The light we observe from these ancient galaxies not only informs us about their properties, but also about the conditions of the intergalactic medium through which it has travelled. Absorption features in the spectra reveal the density, temperature, and composition of gas between galaxies, providing a three-dimensional map of the early universe. By studying these absorption patterns, astronomers can reconstruct how matter was distributed on large scales, how cosmic filaments formed, and how galaxies influence their surroundings through radiation, winds, and outflows. These discoveries also invite philosophical reflection on the nature of cosmic history. The fact that galaxies could form and evolve so rapidly after the universe's birth challenges our assumptions about the pace of cosmic evolution. It suggests that the universe was capable of producing complexity and structure far sooner than our models anticipated. The unexpectedly ancient galaxies reveal that the early universe was not a uniform, slowly evolving landscape but a place of intense activity, rapid growth, and diverse environments. Star formation, galaxy assembly, chemical enrichment, and black hole growth all proceeded at a pace that tests the limits of current theories. Every new observation from the James Webb Space Telescope adds detail to this picture, showing that the universe's history is more intricate and nuanced than previously imagined. As astronomers continue to survey the distant universe, more such galaxies are being identified, each adding pieces to the puzzle of how structure emerged from the primordial darkness. They allow for comparisons between galaxies at different redshifts, helping scientists trace the sequence of cosmic evolution, determine the efficiency of star formation, and assess the influence of early feedback mechanisms on subsequent generations of galaxies. These insights feed directly into our broader understanding of cosmic evolution, bridging the gap between the first few 100 million years after the Big Bang and the universe as we see it today. The discovery of unexpectedly ancient galaxies has already prompted re-evaluation of theoretical models and generated new hypotheses. Some researchers propose that early galaxy formation may have been accelerated by conditions not previously considered, such as variations in dark matter properties, enhanced cooling of gas, or previously unrecognized feedback processes. Others suggest that our measurements of redshift and distance may need even more precise calibration, incorporating new techniques to account for the complex interplay of cosmic expansion and light propagation. Every photon that reaches us from these distant objects carries with it information about the time, place, and conditions in which it was emitted. By carefully analysing this light, astronomers can reconstruct events from billions of years ago, creating a detailed timeline of cosmic evolution. The unexpected maturity of these galaxies emphasises that the universe can surprise us, revealing histories and processes that challenge our expectations and drive the continuous refinement of scientific knowledge. Through the study of ancient galaxies, astronomers are beginning to piece together a more complete picture of the universe's first billion years. These galaxies provide a laboratory for testing theories of star formation, chemical enrichment, galactic assembly, and the growth of black holes. They highlight the importance of observational data in shaping our understanding of the cosmos, and demonstrate that the universe often evolves in ways that are faster, more efficient, and more complex than traditional models would suggest. Every discovery adds a new layer of complexity to the story of the early universe. Some galaxies are already massive and chemically mature, while others are smaller and still forming stars at a rapid pace. This diversity challenges the notion of a uniform, gradual process, and points toward a rich and varied early cosmic environment. The detailed study of these galaxies will continue to refine our understanding of the timeline of cosmic events, from the ignition of the first stars to the formation of large-scale structures that eventually gave rise to galaxies like our own Milky Way. As the James Webb Space Telescope and other advanced observatories continue to probe the distant universe, the census of ancient galaxies will grow, providing increasingly detailed maps of how matter assembled and evolved over time. Each new galaxy discovered at extreme redshift pushes the boundaries of what is considered possible in the early universe, informing theoretical models and challenging assumptions about the pace of cosmic history. These findings demonstrate the ongoing interplay between observation and theory, showing that our understanding of the universe is always provisional, evolving as new evidence emerges. The existence of unexpectedly ancient galaxies ultimately emphasizes that the universe is more dynamic and intricate than previously imagined. Their light carries a story of rapid star formation, early chemical enrichment, and accelerated growth, revealing a cosmos capable of producing complex structures remarkably soon after its beginning. By studying these galaxies in ever greater detail, astronomers are uncovering the mechanisms that governed the universe's first billion years, illuminating the processes that led from the initial hot, dense state of the Big Bang to the vast and richly structured universe we inhabit today. This ongoing exploration reshapes our understanding of cosmic history. It suggests that the timeline of galaxy formation may be shorter and more active than previously thought, that star formation and chemical enrichment could occur far more rapidly, and that the universe's early structures were already exhibiting complexity comparable to that seen much later in cosmic time. The study of unexpectedly ancient galaxies is thus central to modern cosmology, offering a unique window into the processes that built the cosmos, and revealing a universe that is far more efficient, intricate, and surprising in its evolution than previously understood. The observation of these galaxies encourages continued investigation into the interplay of dark matter, baryonic matter, radiation, and gravitational dynamics in shaping the earlier structures. Each galaxy offers clues about the efficiency of star formation, the role of feedback from supernovae and black holes, and the influence of the cosmic environment on growth rates. By building a comprehensive picture from these observations, scientists can refine models of cosmic evolution, making them more accurate in describing both the early universe and the large-scale structures seen in later epochs. The discovery of unexpectedly ancient galaxies continues to challenge our understanding of time, structure, and evolution on cosmic scales. They demonstrate that galaxies could form, grow, and mature far earlier than previously anticipated, forcing astronomers to reconsider the mechanisms governing the earliest periods of cosmic history. As more data is collected, the patterns of early galaxy formation, the pace of star formation, the enrichment of elements, and the growth of supermassive black holes will become clearer, providing a more complete and detailed understanding of the universe's formative years. These galaxies, bright beacons from a time when the universe was still in its infancy, remain central to ongoing research and debate. Observing them allows astronomers to probe conditions that existed nearly 14 billion years ago, providing essential context for understanding how the universe transformed from a hot, nearly uniform state into the vast, structured cosmos of today. Each ancient galaxy offers an independent verification of the processes that shaped the early universe, reinforcing the notion that the cosmic history is far richer and more varied than a simple, linear progression. The study of these galaxies reveals that processes such as star formation, chemical enrichment, galaxy assembly, and black hole growth were not uniform or slow, but dynamic and efficient, producing mature structures far sooner than anticipated. By integrating these observations with theoretical models and simulations, astronomers are constructing a more nuanced picture of the universe's first billion years, capturing the interplay of physics, chemistry, and gravity that forged the cosmos in its earliest epochs. The light from these galaxies continues to arrive at Earth, each photon a messenger from a time when the universe was only a fraction of its current age. Analyzing this light provides precise information about the properties of stars, the composition of gas, the presence of dust, and the history of star formation within each galaxy. The unexpectedly advanced state of these galaxies at extreme redshift forces astronomers to refine their understanding of how quickly stars can form, how efficiently galaxies assemble, and how the universe transitions from simple to complex structures in a remarkably short time. The observations made possible by the James Webb Space Telescope have thus transformed the field of early galaxy studies. The telescope's ability to detect faint infrared light from extreme distances allows for the identification of galaxies that would have been invisible to previous instruments, revealing a population of ancient, massive, chemically evolved systems that challenge standard cosmological models. Each new discovery adds depth to our understanding of the early universe, showing that galaxy formation and evolution proceeded at a pace that was previously unimagined, shaping a cosmos that was vibrant, complex and dynamic from its earliest epochs. Galaxies that appear unexpectedly ancient continue to be a focal point of study, as astronomers seek to understand the processes that could produce such rapid evolution. Investigating their stellar populations, chemical abundances, structural properties and interactions provides critical insight into the efficiency and mechanics of early galaxy formation. The fact that such galaxies exist at redshifts corresponding to times only a few 100 million years after the Big Bang suggests that our theoretical models must accommodate rapid assembly, efficient star formation and early chemical enrichment, while also explaining the growth of massive structures and supermassive black holes. The discovery of these galaxies is also reshaping the questions scientists ask about the early universe. They prompt investigations into whether our understanding of dark matter is complete, whether star formation physics needs to be revised, and whether additional mechanisms, such as early mergers or enhanced cooling of gas, played a role in accelerating galaxy evolution. These questions drive both observational programs and theoretical research, guiding the design of future telescopes, simulations and surveys aimed at exploring the universe's formative years in ever greater detail. Their presence indicates that the early universe was capable of producing mature, massive and chemically enriched galaxies in far less time than previously thought. Each new observation challenges astronomers to refine their understanding of cosmic history, reconcile theoretical models with empirical data, and explore the physical processes that enabled the rapid emergence of complex structures. By studying these galaxies, scientists gain a clearer picture of the mechanisms that shaped the universe's earliest epochs, revealing a cosmos that was already structured, active, and diverse in ways that continue to intrigue and challenge our understanding. These galaxies offer more than just evidence of rapid evolution. They provide a window into the interplay between matter, energy, and gravity in the early universe. By observing the properties of stars, gas, and dust within these galaxies, astronomers can infer how efficiently the first stars formed, how feedback from stellar winds and supernovae influenced subsequent star formation, and how early galaxies merged and interacted. This information is essential for constructing comprehensive models of galaxy formation that can account for both the diversity and the maturity observed at extreme redshifts. The study of unexpectedly ancient galaxies also informs the search for the very first stars, known as population 3 stars, which formed from pristine hydrogen and helium shortly after the Big Bang. While these earlier stars are thought to have been massive and short-lived, the chemical signatures they left behind in subsequent generations of stars provide clues to the processes of early star formation and chemical enrichment. The existence of mature, chemically enriched galaxies at extreme redshifts suggests that population 3 stars had already completed their life cycles and seeded the universe with heavier elements, enabling the rapid formation of subsequent generations of stars. As astronomers continue to explore the distant universe, the population of unexpectedly ancient galaxies will likely grow, offering increasingly detailed insight into the universe's first billion years. Each galaxy adds to a complex narrative of rapid evolution, diverse environments, efficient star formation, early chemical enrichment, and the growth of massive structures. The discovery of galaxies that seem to be older than the universe itself has become one of the most puzzling and fascinating topics in modern astronomy, a phenomenon often referred to as the too old, too early problem. This unexpected observation challenges our understanding of cosmic history and the timeline laid out by the standard cosmological model, which has guided scientists for nearly a century. According to this model, the universe began with a Big Bang roughly 13,800,000,000 years ago. After the initial expansion, it took hundreds of millions of years for the first stars and galaxies to form. Yet observations with the James Webb Space Telescope, which is capable of detecting the faint infrared light from galaxies formed in the earliest epochs of the cosmos, have revealed structures that appear far more developed than theory allows, raising profound questions about how quickly matter could have organized itself into complex forms. The issue arises when astronomers examine the light coming from extremely distant galaxies, light that has travelled for more than 13 billion years before reaching our telescopes. When we observe such light, We are essentially looking back in time, seeing these galaxies as they existed when the universe was only a few 100 million years old. By analysing their properties, such as their mass, brightness, colour, and the abundance of heavy elements, they can estimate how old these galaxies must have been to reach their observed state. The puzzling result is that some galaxies appear to have formed stars at an extraordinary rate, creating massive stellar populations in a time that, according to current models, should have been insufficient. In some cases, the inferred ages of these galaxies seem to exceed the age of the universe at the time their light was emitted, a paradox that cannot be easily explained. One of the key factors in this mystery is the process of galaxy formation itself. Galaxies are not static objects. They grow and evolve over billions of years. According to the standard cosmological model, the first stars formed from clouds of primordial hydrogen and helium a few 100 million years after the Big Bang. These first stars, often called population 3 stars, were massive, hot, and short-lived, and their explosive deaths as supernovae produced the heavier elements necessary for the formation of subsequent generations of stars and galaxies. Over time, gravity pulled together these stars and the surrounding gas to form larger structures, slowly building up the galaxies we observe today. This process, though violent and complex, is predicted to take significant time, with massive, well-organised galaxies emerging only after several 100 million years of continuous star formation and accumulation of matter. The too old too early problem arises when we find galaxies that are not just massive, but also surprisingly mature in their structure and chemical composition, at epochs when the universe should have been far younger and simpler. Observations indicate that some of these galaxies already contain stars with a high concentration of elements heavier than hydrogen and helium, suggesting that multiple generations of stars must have already lived and died to enrich the interstellar medium. For a galaxy to reach such a level of chemical maturity, it must have formed stars at a furious pace almost immediately after the Big Bang, a scenario that stretches the limits of what current cosmology deems possible. This discrepancy between observed properties and theoretical predictions forces astronomers to reconsider how rapidly the universe could assemble complex structures and whether there may be gaps in our understanding of early cosmic physics. The tension between observation and theory becomes more pronounced when we consider the methods used to determine the ages of these galaxies. Astronomers rely on photometric and spectroscopic data, which measure the intensity and distribution of light across different wavelengths. By fitting these data to models of stellar populations, they can estimate the mass, star formation history, and age of the galaxy. However, these models depend on assumptions about the initial mass function of stars, the rate of star formation, and the efficiency of processes like gas cooling and feedback from supernovae. Small changes in these assumptions can produce different age estimates, but even with generous margins of error, some galaxies remain inexplicably old. For example, galaxies observed at a redshift of 10 or higher, corresponding to a time when the universe was only around 400 million years old, sometimes show properties consistent with stellar populations several 100 million years older, suggesting that star formation began almost immediately after the Big Bang. The discovery of these early massive galaxies has been enabled by advances in observational technology, particularly the James Webb Space Telescope. Webb's infrared capabilities allow it to detect the red-shifted light from the earliest galaxies, light that has been stretched into the infrared spectrum due to the expansion of the universe. Previous telescopes, limited to visible and ultraviolet light, could not see these ancient faint galaxies with sufficient clarity. Webb's instruments, including the near-infrared camera and the mid-infrared instrument, provide unprecedented sensitivity and resolution, allowing astronomers to study the composition and structure of galaxies formed within the first few 100 million years. These observations have revealed galaxies with well-defined shapes, large stellar masses, and surprisingly high metallicities, all features that should not exist at such early times according to standard models. The ability to observe these distant galaxies has transformed our understanding of cosmic history and highlighted the gaps in our knowledge about the universe's formative years. One of the most striking examples of the too old too early problem is the discovery of galaxies that appear fully formed when the universe was less than 5% of its current age. These galaxies already contain billions of stars and show evidence of organised structures such as disks or central bulges. Their masses are comparable to mature galaxies in the nearby universe, yet they exist at a time when theoretical models suggest that galaxies should have been small, irregular, and still in the process of forming. The presence of these massive systems challenges the assumed timeline for star formation, galaxy assembly, and the accumulation of matter. It raises fundamental questions about the physics of early star formation, the role of dark matter in structure formation, and the potential for previously unrecognized processes that could accelerate the growth of galaxies. The chemical composition of these early galaxies also presents a significant puzzle. Observations reveal unexpectedly high abundances of elements such as carbon, oxygen, and iron, which are produced by successive generations of stars. To reach this level of enrichment, multiple cycles of star formation and supernova explosions must have occurred in a very short period, suggesting that these galaxies experienced an intense burst of star formation shortly after the universe's birth. The rapid production of heavy elements challenges existing models of stellar evolution and nuclear synthesis, which predict slower enrichment rates. The apparent maturity of these galaxies indicates that the universe may have been more efficient at forming stars and creating chemical complexity than previously believed, calling for revisions to our models of cosmic evolution. Another factor complicating the too old too early problem is the role of cosmic inflation and the expansion of space. According to standard cosmology, the universe underwent a period of extremely rapid expansion in its first fraction of a second, stretching quantum fluctuations into the seeds of large-scale structures. These fluctuations eventually grew under the influence of gravity, forming galaxies and clusters. However, the unexpectedly early appearance of massive galaxies suggests that the initial fluctuations may have been larger or more efficiently translated into matter than current models assume. This possibility could indicate that our understanding of the inflationary period, the behavior of dark matter, or the dynamics of baryonic matter in the early universe is incomplete, opening the door to new theoretical frameworks that could explain the rapid assembly of galaxies. Some researchers have proposed that the too old too early problem might point to a need for alternative cosmological models. For instance, models that include variations in the properties of dark matter or modified theories of gravity could potentially allow for faster structure formation. Other hypotheses suggest that star formation in the early universe could have been more efficient than current models predict, perhaps due to differences in gas cooling, the initial mass function of stars, or feedback processes. Some scientists even entertain the possibility that the age estimates of these galaxies could be affected by systematic errors in the interpretation of light, though the consistency of observations across multiple instruments and wavelengths makes this explanation less likely. Observations of these ancient galaxies also have implications for the study of cosmic reionization, the period when the first luminous objects ionize the neutral hydrogen in the intergalactic medium. Reionization is thought to have begun a few 100 million years after the Big Bang, and to have continued for several 100 million years. The existence of massive early galaxies suggests that significant sources of ionizing radiation were already in place at very high redshifts, accelerating the timeline of reionization. This challenges models of the early universe that assume a slower build-up of ionizing photons and may require a re-evaluation of the processes driving the ionization of intergalactic hydrogen. The interplay between galaxy formation, star formation efficiency, and reionization is therefore central to resolving the too old too early problem. The problem also raises questions about the formation of the first supermassive black holes. Many of these early massive galaxies appear to host black holes with masses of millions or even billions of times that of the Sun, yet the standard model predicts that black holes grow slowly over time through accretion and mergers. The presence of such massive black holes in young galaxies suggests that either black hole formation was unusually rapid in the early universe, or that the mechanisms driving their growth were more efficient than current theories account for. This connects the too old too early problem to another area of cosmic mystery: the origin and rapid growth of supermassive black holes in the universe's infancy. Understanding how these objects could form and co-evolve with galaxies is crucial for a complete picture of early cosmic history. In addition to observational challenges, the too old too early problem highlights the limits of theoretical modelling. Cosmological simulations, such as those that attempt to recreate the evolution of the universe from the Big Bang to the present day, rely on assumptions about the physics of gas, stars, dark matter, and feedback processes. While these simulations have been remarkably successful at reproducing the large-scale structure of the universe and the properties of galaxies at later times, they struggle to account for the early emergence of massive chemically mature galaxies. The discrepancy suggests that certain physical processes, perhaps related to the efficiency of star formation, the interaction between galaxies and their environment, or the behaviour of dark matter, may not be fully captured in current models. The gap between theory and observation therefore drives both the refinement of simulations and the exploration of new physical principles. The observational data also demonstrate that the early universe was more diverse than previously thought. While some regions contain surprisingly mature galaxies, others remain dominated by small irregular systems, indicating that galaxy formation proceeded at different rates in different environments. This heterogeneity challenges the notion of a uniform, predictable timeline for the early universe and suggests that local conditions, such as density fluctuations, gas availability, and feedback effects, played a significant role in shaping galaxy evolution. Recognizing the variety of pathways through which galaxies can form and evolve is essential for resolving the apparent paradox of galaxies that seem too old for their time. Furthermore, the too old too early problem has implications for our measurement of cosmological parameters. The expansion rate of the universe, quantified by the Hubble constant, affects the interpretation of redshift and the inferred ages of distant galaxies. Discrepancies between local measurements of the Hubble constant and values inferred from the cosmic microwave background have already prompted debates about potential revisions to the standard cosmological model. The existence of unexpectedly mature galaxies at high redshifts adds another layer of complexity, suggesting that adjustments to the expansion history or the physics governing early structure formation may be necessary. Reconciling these observations with theoretical models requires careful analysis of both the data and the underlying assumptions. Some astronomers have suggested that the too old too early problem may reveal new physics or processes operating in the early universe that have not yet been accounted for. Possibilities include variations in the properties of dark matter, such as interactions that promote faster clustering of matter, or novel mechanisms for gas cooling and star formation that accelerate the assembly of galaxies. Others propose that unknown sources of energy or radiation in the first few 100 million years could have influenced the pace of cosmic evolution. While speculative, these ideas demonstrate that the problem encourages creative thinking and a re-examination of long-standing assumptions, pushing the boundaries of our knowledge about the universe's first billion years. The discoveries made by the James Webb Space Telescope have been particularly striking in this regard. Webb's ability to observe galaxies at redshifts beyond 10, corresponding to a universe less than 500 million years old, has uncovered numerous candidates for massive chemically mature galaxies. These observations include both photometric data, which measure brightness in different filters, and spectroscopic data, which reveal detailed information about the chemical composition and kinematics of stars and gas. The consistency of these findings across multiple fields of observation and independent instruments strengthens the case that these early galaxies are real and not artifacts of measurement or data analysis. Each new detection adds to the puzzle, reinforcing the need for new theoretical explanations and further observational campaigns. The problem also intersects with our understanding of cosmic chronology. If galaxies can form so quickly and become chemically enriched within a few 100 million years, it suggests that the early universe was capable of producing complex structures on a timescale much shorter than traditionally assumed. This realization forces a re-evaluation of the sequence of events following the Big Bang, including the formation of the first stars, the enrichment of the interstellar medium, and the assembly of large-scale structures. The apparent rapidity of these processes challenges the linear, step-by-step progression envisioned in classical cosmology and hints at a more dynamic, accelerated early evolution of the universe. Moreover, the too old too early problem has sparked debate about the reliability of stellar population models at extreme redshifts. Models used to estimate galaxy ages rely on our understanding of stellar evolution, including how stars of different masses burn their fuel, age, and die. While these models are well tested for stars in the nearby universe, their applicability to the first generations of stars remains uncertain. Variations in metallicity, rotation rates, binary interactions, and initial mass distributions could all influence the inferred ages of galaxies, potentially leading to systematic overestimates. Researchers are actively exploring these uncertainties attempting to refine models and assess whether the apparent paradox could be mitigated by improved understanding of stellar physics in the early universe. The accumulation of evidence for mature galaxies in the universe's first few 100 million years also has consequences for understanding cosmic feedback mechanisms. Feedback from supernovae, stellar winds, and active galactic nuclei plays a critical role in regulating star formation and shaping the evolution of galaxies. In standard models, feedback limits the efficiency of star formation and slows the growth of massive systems. The observation of early massive galaxies suggests that either feedback was less effective in the early universe, or that galaxies found ways to sustain rapid star formation despite energetic outflows. Understanding these dynamics is key to reconciling theory with observation and to constructing a coherent picture of early galaxy evolution. The too old too early problem extends beyond galaxies to other cosmic structures. For example, clusters of galaxies, large-scale filaments, and massive black holes may also have formed earlier and grown faster than predicted. This realization encourages astronomers to look for correlations between galaxy maturity, environmental factors, and large-scale cosmic structures, which could reveal underlying principles governing early universe evolution. By studying these connections, researchers aim to identify the processes that allowed some regions to produce mature galaxies so rapidly while others remained relatively undeveloped. Scientists have long worked to understand the universe, a vast expanse stretching far beyond what the human eye can see, filled with countless galaxies, stars, and cosmic phenomena. In this immense universe, there are mysteries that defy our current understanding, and one of the most puzzling is the problem of galaxies forming unusually quickly in the early periods of cosmic history. Observations from advanced telescopes, especially those capable of detecting very distant and ancient galaxies, have revealed objects that appear far older than expected based on the time elapsed since the Big Bang. These discoveries raise profound questions about the forces shaping the early universe and whether our standard models are missing key components. Among the most intriguing possibilities is the idea that unseen forces, known as dark matter and dark energy, could play a critical role in accelerating the formation of galaxies long before ordinary matter alone could account for their growth. Dark matter, a concept first proposed in the early 20th century after astronomers noticed that the visible matter in galaxies could not account for the gravitational effects observed, has become a cornerstone of cosmology. Though it cannot be seen directly, dark matter exerts gravitational influence on surrounding matter, shaping the formation and movement of galaxies across the universe. Its presence is inferred from the way galaxies rotate and the way light bends around massive clusters, a phenomenon known as gravitational lensing. In the context of early galaxy formation, dark matter may have acted as a scaffold, providing a gravitational framework that allowed normal matter, including gas and dust, to collapse and form stars and galaxies far earlier than conventional models predict. Without dark matter, the process of galaxy formation would likely have taken much longer, leaving the universe with fewer mature structures in its infancy. Dark energy, discovered only in the late 20th century, adds another layer of complexity. Unlike dark matter, which pulls matter together, dark energy is thought to drive the accelerated expansion of the universe. Observations of distant supernovae in 1998 revealed that the expansion rate of the universe is increasing, not slowing as previously assumed. This mysterious form of energy, which now makes up roughly 70% of the total energy density of the universe, exerts a repulsive force that counteracts the pull of gravity on cosmic scales. While dark energy primarily influences the large-scale structure of the cosmos and the expansion of space itself, it may also indirectly affect the pace at which galaxies form. By altering the rate at which space expands in the early universe, dark energy could have created conditions where gas cooled and condensed into stars more efficiently, allowing galaxies to assemble at an accelerated pace. The interplay between dark matter and dark energy creates a cosmic dance that determines how structures evolve over billions of years. Dark matter, clumping under gravity, forms dense regions called halos that act as seeds for galaxy formation. Ordinary matter falls into these halos, cooling and forming stars at rates that can be surprisingly rapid. Dark energy, meanwhile, stretches space between these regions, influencing how quickly these halos grow and merge. In the early universe, when the first galaxies were beginning to take shape, Slight variations in the density of dark matter could have dramatically accelerated the process, concentrating matter in certain regions and allowing galaxies to appear more mature than expected. The combination of these unseen forces may explain why some galaxies observed by instruments like the James Webb Space Telescope appear older than theoretical models based solely on visible matter would allow. One of the key mechanisms by which dark matter could accelerate galaxy formation is through the creation of gravitational wells. These wells are areas of intense gravity caused by concentrations of dark matter, which draw in surrounding gas and dust. As gas falls into these wells, it becomes compressed and heats up, eventually cooling and fragmenting into clouds dense enough to ignite nuclear fusion, the process that powers stars. In regions with higher concentrations of dark matter, this process can happen more quickly and efficiently, producing stars and galaxies earlier than models that do not include dark matter predict. The structure of these dark matter halos also affects the shape and distribution of galaxies, leading to differences in their sizes, densities, and the speed at which they assemble. In addition to dark matter, dark energy's influence on the expansion rate of the universe could create conditions favourable for early galaxy formation in ways that are subtle but significant. While the universe expands, gas clouds cool as they spread out, allowing atoms to combine and form the first stars. If the rate of expansion is slightly different from what standard models assume, this cooling process could occur more efficiently, leading to earlier star formation. Furthermore, dark energy's repulsive effect on large scales could prevent some regions of space from collapsing too quickly, preserving the density fluctuations necessary for galaxies to form in a structured and orderly way. In this sense, dark energy is not merely a force that pushes the universe apart. It also sets the stage for galaxies to emerge and evolve in a cosmic environment that balances expansion with gravitational collapse. Observations of extremely distant galaxies provide indirect evidence that dark matter and dark energy may have played a crucial role in accelerating their formation. Galaxies observed at redshifts greater than 10, meaning their light has taken over 13 billion years to reach us, exhibit properties such as high stellar mass, significant chemical enrichment, and organized structures that suggest they formed rapidly in the first few 100 million years after the Big Bang. These characteristics are difficult to explain if only normal matter and standard physics are considered. Models incorporating dark matter halos and variations in dark energy density provide more plausible pathways for these galaxies to reach such advanced stages of development in a cosmologically brief time span. Simulations of galaxy formation that include dark matter and dark energy effects also offer insight into how early galaxies might have grown so quickly. Computational models allow scientists to recreate the conditions of the early universe and test how variations in dark matter density and the influence of dark energy affect the growth of cosmic structures. These simulations often show that galaxies can form faster and become more massive in regions with dense dark matter concentrations. They also indicate that the repulsive effect of dark energy can help maintain the delicate balance needed for galaxies to merge and interact without disrupting star formation, leading to the complex structures seen in observations. By comparing these models with real data from telescopes, scientists refine their understanding of how unseen forces shaped the early universe. The presence of dark matter and dark energy may also help explain other surprising features of early galaxies, such as their chemical composition. Stars produce heavier elements over time through nuclear fusion, and galaxies that appear mature early in the universe often show signs of significant enrichment in these elements. This suggests that star formation was not only rapid but sustained, occurring in bursts that built up the chemical complexity of galaxies sooner than expected. Dark matter halos provide the gravitational stability needed for multiple generations of stars to form within the same galaxy, while the influence of dark energy ensures that these galaxies remain coherent structures despite the universe's expansion. Together, these forces create environments where galaxies can evolve chemically as well as structurally, producing mature systems in a relatively short period. Alternative explanations involving dark matter and dark energy also intersect with other theoretical ideas in cosmology, such as modifications to the standard model of particle physics or variations in the properties of gravity itself. Some scientists propose that dark matter could include exotic particles that interact in ways not yet fully understood, potentially enhancing the rate of galaxy formation. Others suggest that dark energy might not be constant, but could have changed over time, creating periods of accelerated growth for cosmic structures. While these ideas remain speculative, they illustrate the profound influence that unseen forces may have had on shaping the universe we observe today. Evidence for the accelerating effects of dark matter and dark energy is not limited to the earliest galaxies. Observations of large-scale structures, such as galaxy clusters and superclusters, reveal patterns of distribution that match predictions from models incorporating these invisible forces. Galaxies tend to cluster along filaments of dark matter, forming vast cosmic webs with voids in between where matter is sparse. The speed at which these structures formed and evolved can inform scientists about the underlying physics driving the process, including the roles of dark matter and dark energy. By understanding how these forces influence the growth of cosmic architecture over billions of years, researchers can better interpret the properties of the oldest galaxies and the conditions that allowed them to emerge so quickly. The interaction between dark matter and dark energy may also provide insights into the puzzling phenomenon known as the too old, too early problem, in which some observed galaxies appear older than the universe itself, according to standard cosmological calculations. If dark matter accelerates star formation and galaxy assembly, while dark energy subtly influences the timing and distribution of these processes, it becomes possible for galaxies to reach apparent ages that seem anomalously high. This does not necessarily contradict the Big Bang model, but suggests that our understanding of the forces shaping cosmic evolution is incomplete without accounting for these invisible components. The combined effects of dark matter and dark energy could reconcile the apparent discrepancy between observed galaxy ages and theoretical predictions, highlighting the importance of these unseen forces in the cosmic timeline. Furthermore, the study of dark matter and dark energy's influence on early galaxy formation has implications for our understanding of the universe's ultimate fate. If these forces played a significant role in accelerating the assembly of galaxies in the early universe, they may also determine how galaxies continue to evolve and interact over the next billions of years. Dark energy, in particular, influences the rate at which the universe expands, affecting whether galaxies will eventually drift apart or continue to merge into larger structures. Dark matter, by providing the gravitational backbone for galaxy formation, may continue to shape the distribution and dynamics of matter across the cosmos, even as dark energy drives space itself to expand ever faster. By studying their effects in the early universe, scientists gain insight into both the past and future trajectories of cosmic evolution. Observational campaigns aimed at detecting the signatures of dark matter and dark energy in the early universe are becoming increasingly sophisticated. Telescopes like the James Webb Space Telescope, the Hubble Space Telescope, and ground-based observatories employ multiple wavelengths to probe the formation and growth of galaxies across cosmic time. By measuring properties such as stellar mass, star formation rates, chemical composition, and galaxy clustering, researchers can infer the underlying influence of dark matter halos and the expansion effects driven by dark energy. These observations, combined with theoretical modelling, help scientists understand how unseen forces accelerated the emergence of mature galaxies in what appears to be a remarkably short period after the universe's birth. Theoretical frameworks for understanding dark matter and dark energy continue to evolve. Various models propose different types of dark matter, from weakly interacting massive particles to axions or sterile neutrinos, each with distinct implications for early galaxy formation. Similarly, dark energy is modelled as a cosmological constant, a dynamic field, or a modification of general relativity, affecting predictions about the rate of expansion and the timing of cosmic structure formation. The interplay of these models with observational data on ancient galaxies helps refine our picture of the early universe, and suggests that the acceleration of galaxy formation may be a natural consequence of the interaction between these invisible forces. The rapid formation of early galaxies influenced by dark matter and dark energy may also shed light on the reionization era, a period roughly between 400 million and 1 billion years after the Big Bang, when the first stars and galaxies ionized the surrounding hydrogen gas. This phase transformed the universe from a mostly neutral state into one that is largely ionized, allowing light to travel freely across space. Accelerated galaxy formation due to dark matter and dark energy could have contributed to an earlier and more efficient reionization process, impacting the visibility of distant galaxies and the temperature of the intergalactic medium. Observing the signatures of this epoch provides additional evidence for how unseen forces shaped the timeline of cosmic history. Another fascinating aspect is the connection between dark matter, dark energy, and galaxy morphology. Galaxies come in a variety of shapes, from spiral and elliptical to irregular forms, and the environment in which a galaxy forms can influence its final structure. Dense dark matter halos may favour the formation of certain types of galaxies by directing the flow of gas and regulating star formation, while the expansion driven by dark energy can affect the interactions between neighbouring galaxies. In this way, unseen forces not only accelerate galaxy formation, but also influence their physical appearance and internal dynamics. Cosmic simulations that include dark matter and dark energy also reveal the importance of feedback mechanisms in regulating star formation. Supernova explosions, black hole activity, and radiation from massive stars can push gas out of galaxies, temporarily halting further star formation. The strength of these feedback processes is influenced by the surrounding dark matter halo, which determines how much gas can be retained and how quickly it can cool and collapse again. Dark energy, by affecting the expansion rate, also modulates the density of intergalactic gas and the timing of mergers, contributing to the overall pace at which galaxies evolve. The combination of gravitational scaffolding from dark matter and expansion effects from dark energy creates a complex environment in which galaxies can grow rapidly while maintaining stability. Observational anomalies, such as unexpectedly bright and massive galaxies in the early universe, continue to challenge traditional models and highlight the potential role of dark matter and dark energy in solving these puzzles. By providing a gravitational framework and influencing the expansion of space, these unseen forces offer a coherent explanation for how galaxies could form quickly and reach advanced stages of development within the first few 100 million years. Ongoing research aims to quantify these effects more precisely, using increasingly sensitive instruments and more detailed simulations to unravel the mechanisms behind accelerated galaxy formation. The influence of dark matter and dark energy on early galaxy formation also intersects with questions about the nature of the universe itself. If these forces can significantly accelerate the assembly of galaxies, it raises questions about the initial conditions of the universe, the distribution of matter and energy, and the physical laws governing cosmic evolution. Studying these effects helps refine estimates of the universe's age, the timeline of cosmic structure formation, and the sequence of events leading from the Big Bang to the complex cosmos observed today. By considering the role of unseen forces, scientists can construct models that better match observations and provide a more comprehensive understanding of the universe's history. The importance of dark matter and dark energy in shaping the early universe extends to the study of cosmological parameters, such as the Hubble constant, which measures the rate of expansion, and the matter density parameter, which quantifies the proportion of matter in the universe. Variations in these parameters can influence the predicted timing of galaxy formation and the growth of large-scale structures. Incorporating the effects of dark matter halos and dark energy into cosmological models allows for more accurate predictions of the properties of early galaxies, helping to reconcile apparent discrepancies between observations and theory. In addition, alternative explanations involving dark matter and dark energy provide a framework for understanding the diversity of galaxy formation histories. Not all galaxies form at the same rate or in the same manner, and variations in dark matter density, dark energy influence, and local environmental conditions can lead to a wide range of outcomes. Some regions of the universe may have experienced accelerated formation, producing massive and mature galaxies early on, while others formed more slowly, resulting in less evolved systems. This diversity is observed in the population of high redshift galaxies, which show a mix of ages, masses, and chemical compositions, reflecting the complex interplay of unseen forces in shaping cosmic history. The potential of dark matter and dark energy to accelerate early galaxy formation also has implications for understanding the formation of supermassive black holes. These black holes, found at the centres of many galaxies, including some observed in the early universe, must have grown rapidly to reach billions of solar masses within a few 100 million years. The presence of dense dark matter halos could have facilitated the accumulation of gas and the formation of massive stars, which in turn collapsed into black holes. Dark energy's influence on cosmic expansion may have allowed these structures to remain in high-density environments conducive to rapid growth, providing a plausible explanation for the existence of supermassive black holes and very young galaxies. The combined effects of dark matter and dark energy highlight the importance of considering unseen forces when interpreting cosmic observations. Without accounting for these components, models struggle to explain the speed and complexity of early galaxy formation, the chemical enrichment of ancient galaxies, and the emergence of large-scale cosmic structures. By including dark matter halos and the influence of dark energy, scientists can develop more accurate and comprehensive models of the early universe, providing insights into the processes that allowed galaxies to assemble quickly and mature in what appears to be an unusually short time. The study of dark matter and dark energy continues to push the boundaries of astrophysics and cosmology. As observational techniques improve and theoretical models become more sophisticated, researchers are gaining a clearer picture of how these unseen forces shaped the universe. Future missions and instruments will provide even deeper views into the early cosmos, potentially revealing the intricate ways in which dark matter and dark energy accelerated the formation of galaxies and other cosmic structures. Understanding these processes is essential for reconstructing the history of the universe and for exploring the fundamental physics governing its evolution. Alternative explanations involving dark matter and dark energy also emphasize the interconnectedness of cosmic phenomena. The growth of galaxies is not an isolated process, but is influenced by the surrounding environment, the distribution of matter, and the expansion of space itself. Dark matter provides the gravitational backbone, shaping the flow of gas and the assembly of stars, while dark energy influences the timing and efficiency of these processes. Together, these forces create conditions in which galaxies can form more quickly than previously thought, offering a compelling solution to the mysteries of the early universe. In conclusion, the idea that unseen forces such as dark matter and dark energy could accelerate early galaxy formation provides a powerful framework for understanding why some galaxies appear older and more developed than expected. By shaping the gravitational landscape, influencing the expansion of space, and regulating the flow of gas and stars, these forces may have allowed galaxies to assemble rapidly in the first few 100 million years after the Big Bang. Observations of high redshift galaxies, combined with theoretical models and simulations, continue to refine our understanding of these processes, revealing the profound impact of dark matter and dark energy on the history and evolution of the cosmos. This line of investigation remains one of the most exciting frontiers in modern astrophysics, offering the possibility that the universe's earlier structures were shaped not only by the familiar laws of matter and gravity, but also by the hidden influence of forces that we can detect only through their effects on the cosmos. As telescopes probe deeper into space and simulations become ever more detailed, the role of dark matter and dark energy in accelerating galaxy formation will continue to be a central question, shedding light on how the universe grew from a near-uniform sea of gas into the richly structured cosmos we observe today. The implications extend beyond understanding individual galaxies. They touch on the very nature of the universe and the physical laws that govern it. If dark matter and dark energy were capable of accelerating early galaxy formation, they may also have influenced the distribution of cosmic structures, the timing of star formation, and the evolution of chemical elements, shaping the universe in ways that challenge traditional expectations. By exploring these alternative explanations, scientists aim to construct a more complete and nuanced picture of the universe, one in which unseen forces play a crucial role in shaping the earliest chapters of cosmic history. The study of these unseen forces also opens the door to new discoveries about the fundamental nature of matter and energy. Understanding how dark matter interacts with ordinary matter and how dark energy drives cosmic expansion could reveal previously unknown aspects of physics, potentially leading to breakthroughs in our understanding of the universe. As research continues, the acceleration of early galaxy formation may become not only a key to explaining observational anomalies, but also a window into the deeper laws that govern the cosmos. Dark matter and dark energy effects are therefore central to many of the most pressing questions in cosmology. They provide a coherent explanation for the rapid assembly of galaxies, the emergence of mature structures in the early universe, and the chemical complexity observed in ancient systems. By shaping both the gravitational landscape and the rate of cosmic expansion, these unseen forces offer a solution to the too old, too early problem and highlight the intricate interplay between visible and invisible components of the cosmos. Cosmic inflation is a concept that has been central to our understanding of the early universe for several decades. It is the idea that, in the first fraction of a second after the Big Bang, the universe expanded at an extraordinary rate, far faster than the speed of light, in a process that smoothed out irregularities and spread matter across space. This concept, while still theoretical, has been used to explain why the universe appears so uniform on large scales, why the cosmic microwave background radiation is so smooth, and why structures like galaxies eventually formed. Cosmic inflation, in its essence, proposes that the universe did not simply expand steadily from a dense point. Instead, there was a sudden, explosive growth in size, taking the universe from a microscopic scale to one that could already host the seeds of galaxies and clusters in an almost instantaneous instant, measured in terms of fractions of a second, a period known as the inflationary epoch. During this epoch, which is thought to have lasted less than a trillionth of a second, the universe grew enormously, stretching tiny quantum fluctuations into regions large enough to influence the formation of matter on the scale of galaxies. These quantum fluctuations, infinitesimal variations in density, were magnified by inflation, becoming the seeds from which all cosmic structures, including galaxies, galaxy clusters, and even superclusters, eventually grew. This mechanism provides a plausible explanation for the uniformity we see in the cosmic microwave background. The afterglow of the Big Bang, which is measured to be almost identical in every direction to 1 part in 100,000. Without inflation, these variations would have been far too large or too chaotic to produce the orderly structures observed in the modern universe. Cosmic inflation also addresses a major puzzle in cosmology known as the horizon problem, which is the question of how regions of space that are far apart and seemingly never in causal contact could have nearly identical temperatures. If the universe had expanded slowly, distant regions could not have exchanged information or energy, yet the cosmic microwave background shows remarkable uniformity. Inflation provides a solution by suggesting that before the rapid expansion, all regions were indeed in contact and in thermal equilibrium. Then, as inflation stretched the universe, these regions were moved far apart, retaining their uniform conditions despite now being separated by enormous distances. This stretching of space also helps explain the flatness problem, which concerns the overall geometry of the universe. Observations suggest that the universe is nearly flat, meaning that the sum of the angles in a triangle drawn across cosmic scales is very close to 180 degrees. Without a rapid inflationary phase, it would have been exceedingly improbable for the universe to appear as flat as it does today. Inflation stretches any initial curvature, smoothing the geometry to an almost perfectly flat state. However, while cosmic inflation successfully explains many large-scale properties of the universe, questions remain when it comes to the formation of extremely ancient galaxies and structures that seem to exist earlier than standard cosmological models predict. Observations from instruments like the James Webb Space Telescope have revealed galaxies that appear to be fully formed less than 300 million years after the universe began, which is only about 2% of the current age of the universe, estimated to be around 13,800,000,000 years. These early galaxies appear surprisingly massive and structured, with well-defined shapes and stars that show chemical enrichment indicative of previous generations of stars, suggesting that star formation and galaxy assembly occurred very rapidly. This presents a challenge. How could such complex systems form in such a short cosmic time span? Could the inflationary epoch have played a role in setting the stage for these ancient structures, accelerating the processes that led to their rapid assembly? One possibility is that the quantum fluctuations magnified during inflation were not just minor irregularities, but may have been larger or more concentrated in certain regions, creating hotspots of higher density. These dense regions would have more material to collapse under gravity, forming stars and galaxies earlier than in regions with lower density. The distribution and scale of these fluctuations are encoded in the cosmic microwave background, but subtle variations may allow for pockets of the universe to evolve faster than the average predictions of standard cosmology. Some cosmologists suggest that rare regions of enhanced density could collapse into massive structures within just a few 100 million years, producing the kinds of ancient galaxies that the James Webb Space Telescope has detected. These galaxies may appear old, not because the universe is older than we think, but because inflation created conditions that allowed for accelerated formation in specific areas, a statistical outcome that becomes more probable when considering the enormous scale of the universe. Another important aspect is the influence of dark matter, which interacts gravitationally but not electromagnetically, meaning it does not emit, absorb, or reflect light. Dark matter is believed to make up about 27% of the universe's total energy content, while ordinary matter accounts for only about 5%. During and after inflation, dark matter would have clumped together more efficiently than ordinary matter, forming gravitational wells into which normal matter could fall. These dark matter halos would provide the scaffolding necessary for galaxies to assemble rapidly. In regions where dark matter density was higher due to the amplified quantum fluctuations, galaxy formation could have proceeded far faster than average, potentially explaining why some galaxies appear fully formed at times when standard models predict only small protogalaxies should exist. In this view, cosmic inflation sets the initial conditions, and dark matter guides the assembly of matter into observable structures, working together to accelerate cosmic evolution. Cosmic inflation might also have implications for the chemical enrichment of early galaxies. Stars form from gas, primarily hydrogen and helium, but through nuclear fusion, stars produce heavier elements such as carbon, oxygen, and iron. When the first generations of stars explode as supernovae, they release these elements into the surrounding medium, enriching the gas for subsequent star formation. If inflation created regions with higher density, star formation could have begun sooner and proceeded more rapidly in these areas, leading to an accelerated cycle of star birth and death. This would explain why we observe chemical signatures in some early galaxies that suggest multiple generations of star formation had already occurred within the first few 100 million years. The combination of inflationary density enhancements and dark matter halos could have provided both the raw material and the gravitational framework needed for these accelerated processes. The scale and timing of inflation are also relevant. The universe expanded from subatomic scales to macroscopic scales almost instantly during inflation, which means that the initial density fluctuations were stretched over distances much larger than the observable universe today. These fluctuations influence the distribution of matter at later times, determining where galaxies and clusters eventually form. Small differences in the amplitude of these fluctuations could lead to variations in the rate of structure formation across different regions. In areas where the fluctuations were slightly stronger, matter would collapse faster, leading to earlier galaxy formation. This perspective suggests that what appears to be a challenge to standard cosmology might instead be an expected statistical outcome of inflationary physics, highlighting the uneven, patchy nature of cosmic evolution. Cosmic inflation also predicts a spectrum of gravitational waves, ripples in the fabric of space-time that could leave subtle imprints on the distribution of matter. If these primordial gravitational waves influenced the motion of matter in the early universe, they could have helped concentrate gas and dark matter in certain regions, further enhancing early galaxy formation. Detecting these gravitational waves is extremely challenging, but ongoing and future experiments aim to observe their effects indirectly through patterns in the cosmic microwave background and in large-scale structure surveys. Confirmation of such effects would provide strong evidence linking inflation directly to the formation of ancient cosmic structures. There is also the possibility that the parameters of inflation are not fixed but can vary, leading to different inflationary histories in different regions of the universe. In some models, inflation may have lasted slightly longer or shorter in different patches, creating variations in density and temperature that influence the pace of galaxy formation. Some patches may have experienced conditions conducive to rapid star formation, while others evolved more slowly. This variation could explain why ancient galaxies seem to be outliers in the cosmic timeline. They formed in regions where inflation created particularly favourable conditions for early structure formation. Moreover, inflationary theory is closely connected to the concept of a multiverse in some models. If inflation continues indefinitely in some regions while ending in others, it could produce a vast array of bubble universes with slightly different physical conditions. Our observable universe would be just one of these bubbles, and the ancient galaxies we see may be the result of local conditions that were unusually conducive to rapid formation. While speculative, this idea highlights how inflation could provide the framework for understanding not only the general uniformity of the cosmos, but also exceptional cases that appear to defy conventional timelines. In addition, inflation may help explain the existence of massive black holes observed in the early universe. Some ancient galaxies contain supermassive black holes with masses of hundreds of millions or even billions of times the mass of our Sun. Standard formation scenarios struggle to account for how such enormous objects could form in less than a few 100 million years. Inflation, by creating regions of enhanced density, may have accelerated the collapse of gas and dark matter, producing the seeds for these supermassive black holes far earlier than expected. Once formed, these black holes could influence galaxy growth through feedback processes, regulating star formation and shaping the morphology of their host galaxies. Observational evidence continues to challenge and refine our understanding of the relationship between inflation and ancient cosmic structures. Telescopes like the James Webb Space Telescope, along with future observatories such as the Nancy Grace Roman Space Telescope and ground-based facilities, will provide more detailed data on the earliest galaxies. These observations will help determine whether the accelerated formation of these ancient structures can be fully explained by inflation and dark matter, or whether additional physics, such as modifications to our understanding of gravity or the properties of dark energy, is required. Inflation offers a compelling framework, but it is not the only possible explanation, and the interplay between theory and observation is crucial for advancing our understanding of these early epochs. Some scientists also consider alternative scenarios that complement inflation. For example, variations in the rate of cosmic expansion due to dark energy, or interactions between dark matter and ordinary matter, could create conditions favourable for early galaxy formation. Inflation sets the initial stage by establishing the large-scale structure and density fluctuations, but the subsequent evolution of the universe depends on a combination of physical processes, including cooling of gas, star formation efficiency, feedback from supernovae, and the merging of protogalaxies. The earliest galaxies likely formed through a complex combination of these mechanisms, and inflation provides the underlying structure upon which they acted. The role of cosmic inflation in explaining ancient structures also connects to the study of reionization, a period when the first stars and galaxies ionized the neutral hydrogen that filled the universe. Observations indicate that reionization began as early as 400 million years after the Big Bang, suggesting that stars and galaxies formed rapidly enough to produce significant amounts of ultraviolet radiation. Inflationary density fluctuations may have influenced where reionization occurred first, creating regions of intense star formation that drove the ionization process. The study of these regions provides insight into how inflation shaped the early universe and set the pace for the emergence of complex structures. Another consideration is the role of mergers in early galaxy formation. Ancient galaxies may have assembled not only through local star formation, but also by merging with smaller protogalaxies. Inflation-created density variations could have increased the probability of early mergers in certain regions, allowing galaxies to grow rapidly in both mass and complexity. These mergers would also trigger bursts of star formation, further accelerating chemical enrichment and structural development. The combination of inflationary initial conditions and subsequent mergers could produce the highly evolved galaxies observed at very high redshifts, which otherwise appear unexpectedly mature for their age. Inflation also has implications for the distribution of voids and filaments in the cosmic web, the large-scale structure of the universe. The same density fluctuations amplified during inflation that lead to early galaxy formation also determine the locations of vast empty regions, known as voids, and dense, elongated structures, known as filaments, connecting galaxies and clusters. The cosmic web, as revealed by surveys of galaxies across billions of light-years, reflects the primordial patterns set during inflation. By understanding these patterns, scientists can trace the history of structure formation and identify regions where early galaxies were more likely to appear. The interplay between cosmic inflation and the cosmic microwave background remains crucial. Detailed measurements of the temperature fluctuations and polarization patterns in the cosmic microwave background provide constraints on inflationary models, including the shape, duration, and energy scale of inflation. These constraints influence predictions about the size and distribution of density fluctuations, which in turn affect when and where galaxies form. Comparing observations of ancient galaxies with these predictions allows scientists to test whether inflation alone can account for accelerated structure formation, or if additional physics is needed. Cosmic inflation also relates to the concept of non-Gaussianity, the degree to which the distribution of density fluctuations deviates from a simple bell curve. If certain regions of the early universe had unusually high density due to non-Gaussian fluctuations, these regions would collapse faster under gravity, producing ancient galaxies earlier than the average predictions. Detecting non-Gaussianity in the cosmic microwave background, or in the large-scale distribution of galaxies, would provide evidence that inflation directly influenced the accelerated formation of structures. Inflationary theory has been developed in many forms, with models such as chaotic inflation, new inflation, and hybrid inflation proposing different mechanisms and energy potentials for the inflaton field, the hypothetical field driving inflation. Each model predicts slightly different outcomes for the distribution and amplitude of primordial density fluctuations. By comparing these predictions with observations of ancient galaxies, cosmologists can refine their understanding of which inflationary scenarios are consistent with the early formation of massive, chemically enriched structures. The discovery of ancient galaxies has also prompted renewed interest in the physics of the inflaton itself. If the inflaton field had certain properties, such as a potential energy curve that allowed for rapid fluctuations or brief pauses in expansion, it could create conditions for localized accelerated structure formation. These fine details of the inflationary process may be essential for explaining why some galaxies appear more evolved than expected in the earliest epochs of the universe. Inflation's influence on cosmic topology, the overall shape and connectivity of space, may also play a role. Certain topological features could concentrate matter in ways that promote early galaxy formation, producing regions where structures assemble faster. While direct evidence for such topological effects is difficult to obtain, they remain a theoretical possibility that could help explain anomalously ancient galaxies. The scale of inflation also means that even extremely rare events, such as regions of unusually high density, become statistically significant. In a universe with billions of galaxies and vast expanses of space, rare inflation-enhanced regions would inevitably produce the earliest and most massive galaxies. This statistical perspective reconciles the existence of ancient galaxies with inflationary theory without requiring a fundamental revision of cosmology. These galaxies are simply the tail end of the distribution of early structures, where conditions happen to be just right for rapid formation. Cosmic inflation also interacts with baryon acoustic oscillations, the ripples in the density of matter created by sound waves in the early universe. These oscillations influence the spacing and distribution of galaxies and can affect the timing of structure formation. Inflation sets the initial conditions for these oscillations, determining their amplitude and wavelength, which in turn shapes the rate and pattern of early galaxy assembly. The connection between inflation and cosmic acceleration is further complicated by dark energy, which dominates the current expansion of the universe. While inflation itself was a temporary phase of rapid expansion, its principles inform our understanding of how energy fields can drive expansion. Some models suggest that early forms of dark energy or vacuum energy may have contributed to localized acceleration in certain regions, enhancing the formation of ancient structures. The interplay between inflation, dark matter, and dark energy creates a rich framework for exploring how the earliest galaxies could appear older and more massive than expected. In addition to observational studies, simulations play a key role in exploring inflation's impact on early structure formation. Cosmologists use supercomputers to model billions of particles and the evolution of matter from the inflationary epoch to the present day. These simulations show that small variations in initial conditions, amplified by inflation, can lead to significant differences in galaxy formation timing. By matching simulated galaxy populations with observed ancient galaxies, scientists can test whether inflation alone is sufficient to produce the rapid assembly seen in the earliest cosmic structures. Inflationary models also provide insight into the rarity and distribution of ancient galaxies. While most regions of the universe follow the average timeline of structure formation, some patches, influenced by the initial conditions of inflation, evolve faster. These rare regions account for the small fraction of galaxies that appear surprisingly old for their redshift. Observing more of these galaxies across different fields of view helps build a statistical picture of how inflation influenced the early universe. The role of cosmic inflation in shaping the earlier structures is therefore multifaceted. It establishes the initial density fluctuations that guide matter assembly, interacts with dark matter to form gravitational scaffolds, influences star formation and chemical enrichment, and affects the large-scale topology of the universe. Its effects persist across cosmic time, shaping the pattern of galaxies, clusters, and voids observed billions of years later. By studying ancient galaxies, cosmologists are testing the limits of inflationary theory and refining our understanding of the processes that created the universe's first complex structures.